Hey everyone! Welcome to the ultimate course on mastering Pytest and test strategies for your projects. Get ready to dive into a dynamic learning experience where you'll gain essential skills for writing effective tests, organizing your code, and implementing robust test strategies. We'll explore everything from creating test functions to advanced features like fixtures and parameterization. And I'm super excited to share hands-on coding exercises that will really reinforce your learning. So, make sure you stick around until the end for a final project that tests everything you've learned. Oh, and don't forget to check the description for a link to our GitHub repository with all the code. Now, let's get started. Pytest provides a powerful and user-friendly framework for writing and executing tests in Python. So today, we're going to dive deep into the mechanics of Pytest. We'll cover how to create test functions, organize your tests, and explore some of those advanced features that make your testing process not just effective, but honestly, pretty enjoyable too. Let's kick things off. First, it's important to know that writing tests helps ensure your code behaves as expected. Okay, ready? Let's jump into creating your first test function. You'll want to start by making sure Pytest is installed. If you haven't done that yet, no worries. Just run pip install pytest in your terminal. Perfect. Now, let's create a new file for our tests. We can name it something like test_sample.py. In this file, we'll define a simple function, say def test add, and within that, we can use assert statements to check if values match, like asserting that 1 + 1 = 2. Now we can run our tests by simply typing pytest into the terminal. Easy, right? You'll see output showing that your test passed. Now, organizing your tests is key, so feel free to group related tests into classes or folders. And oh, don't forget the rich feature set Pytest brings along, like fixtures for setting up contexts, or even parameterizing your tests for extra coverage with different inputs. By the end of this, you'll be super equipped to develop a robust testing strategy. Now, I can't wait for you to experience how handy and efficient Pytest can be. It'll make your testing experience so much smoother. Now, let's dive into creating our very first test functions using Pytest. We're going to define two essential operations, addition and subtraction. All right, our first function, test_addition, checks if the sum of 1 and 1 = 2. It's a simple verification of addition. Super easy. Then we have test_subtraction, which verifies that when we subtract 1 from 2, we get 1. Now notice how these functions start with test? This is really important because it lets Pytest automatically recognize and run them when we execute our test suite. So, when we run this script with Pytest, it will execute both of these test functions and report the results back to us. If both assertions are true, the tests pass, which is a green light that our basic arithmetic operations are working just perfectly. But if any assertion fails, Pytest steps in, giving us a clear report on which test case didn't meet the expected outcome. This straightforward approach to writing and running tests is super fundamental to ensure our code behaves as intended. It really lays the groundwork for more complex scenarios that we'll explore later on. Now let's dive into the exciting world of testing our calculator functionality. We'll kick things off by creating a test file named test_calculator.py. This file will house all our tests for the calculator module. In here, we'll define a bunch of functions, each one dedicated to testing a specific math operation: addition, subtraction, multiplication, and division. We're harnessing the power of the Pytest framework, which is pretty cool because it automatically recognizes any function that starts with test_ as a test case. Each of these functions will contain assertions to check that our expected outcomes are indeed accurate based on different inputs. For instance, our test_addition function will verify specific sums are correct, while test_subtraction will ensure our subtraction logic is performing just as we want it to. Now, let's talk about the test division function. This is where it gets interesting. We'll incorporate some error handling using Pytest.raises, which is super important because it ensures our code properly handles situations like division by 0. Oh no! This way, we raise a zero division error, showing that we're not just testing for the usual output, but also preparing our code for those tricky error conditions, enhancing its robustness. Plus, by using a fixture to create an instance of our calculator class, we keep things clear and cut down on redundancy, making sure all our test functions can share the same setup seamlessly. Isn't that neat? Now, let's dive into how we can run and check our tests using Pytest. First up, we need to navigate to the project directory in our terminal, and here, super important, you'll type pytest followed by the file name. In our case, that's tests/test_calculator.py. Okay, when you hit enter, this command prompts Pytest to gather all those test functions you've defined in that file, and it gives you feedback on how they're performing. As the tests kick off, you'll see this colorful output pop up. A dot? That means a test has passed. An F marks a failure, and whoa, if you see an E, it indicates there's an error. Now here's where it gets really helpful. If there's a failure, Pytest gives super detailed feedback. It tells you exactly which test failed and why. For instance, let's say we hit a snag because of dividing by 0. Pytest will clearly point out that the test_division has failed with a 0 division error. This summary info, it's crucial for quickly spotting and fixing issues in your tests, which helps keep our code quality high as we're developing our application. By consistently running and reviewing these tests, we're creating a robust testing environment that ensures our code behaves just like we expect it to. Next, we will write a simple fixture that allows us to set up and share sample data between tests. This fixture, named sample data, is defined using the @pytest.fixture decorator, which tells Pytest that this function will provide a fixture for our tests. The fixture returns a dictionary containing a sample data structure that includes an ID of 1 and a name set to Alice. Now, let's see how we can utilize this fixture within our test function. We create the function testDataAccess, which accepts sample data as an argument. This is how we gain access to the shared data provided by our fixture. Inside the test function, we perform assertions to check that the values in sample data match our expectations, ensuring that our data is correctly initialized. By leveraging fixtures like this, we streamline our tests, making them cleaner and more focused on the actual validation of functionality rather than on setup and teardown procedures. This organized approach helps in maintaining and scaling our tests as our codebase evolves. Now let's dive into how we can implement parameterization in our tests using Pytest. This feature lets us run a test function multiple times with different data sets, which is super useful for validating functionality under various conditions. It really makes testing a breeze. In our example, we're going to use the @pytest.mark.parameterize decorator to set up 3 parameters: A, B, and expected. Each tuple in the list will represent a different test case, where A and B are the inputs for our test addition function, which performs the addition operation. So what happens is Pytest will run the test addition function 4 times, once for each data tuple we provide. This is a game changer because it cuts down on code duplication. We only need to write the assertion for the expected outcome a single time. Inside the function, we check that the sum of A and B matches the expected result. And this not only streamlines our code, but also boosts its readability and maintainability. Plus, if we want to expand our tests, we can just add more tuples to the list. Overall, parameterization is a powerful feature that really simplifies testing scenarios by managing multiple input values efficiently. So go ahead and use this in your next Pytest setup. Now, let's dive into enhancing our assertions in Pytest to provide clearer feedback. We start by defining the test addition function, which performs a simple addition operation to check if the result equals 2. What's cool here is that we've added a custom error message to our assertion. This message will pop up if the test fails, showing us not just that it failed, but exactly what the expected outcome was compared to what we actually got. Next, we'll create a test subtraction function to handle subtraction. Just like our addition test, we assert that the result of 5 minus 2 equals 3, and we throw in another custom message for clarity if something goes wrong. This approach of adding detailed feedback through messages really streamlines the debugging process, helping to quickly highlight where the discrepancies are, which makes our tests way more informative and effective. And this becomes especially handy in larger projects, where being able to pinpoint issues swiftly can save a huge amount of development time. Now, let's dive into how we can run specific tests using Pytest. When you're working on larger applications, executing the entire test suite can take a bit longer than we'd like. But don't worry, Pytest makes our lives easier with a neat feature that lets you run just a specific test or even a subset of tests based on their names. So, how do we do this? It's simple. You just use the -k option followed by the name of the test you want to execute. For instance, if you're itching to run the test function called test addition, you'd pop open your terminal and type pytest-k test addition. This command tells Pytest to search for that specific test and run it, ignoring all the others. How cool is that? This feature is super helpful when you're focusing on debugging or validating specific functionality. It saves you tons of time, allowing you to zero in on what matters without waiting for the full suite to run. So, by filtering your test executions this way, you make your workflow not just more efficient, but also way more manageable. As your codebase grows, trust me, you're gonna appreciate this. Now let's implement a simple calculator module that performs some basic arithmetic, shall we? The calculator class will define 4 essential methods: add, subtract, multiply, and divide. Each of these methods takes 2 parameters, a and b, which represent the numbers we're going to work with. So for addition, the add method simply returns the sum of a and b. Easy enough, right? And then we have the subtract method, which gives us the difference between these two numbers. Now for multiplication, we'll use the multiply method. It's straightforward, just returning the product of those two numbers. But division, that gets a bit trickier. The divide method needs to check if b is 0 before it tries to perform the operation. We definitely want to avoid that dreaded 0 division error. If b turns out to be 0, it raises this error with a clear message. This helps our program handle potential issues gracefully. Next up, we're going to create a test file named test_calculator.py to make sure our calculator does its job properly. In this test file, we'll set up a fixture that creates an instance of the calculator class, and we can reuse this instance across different test functions. By doing this, we'll systematically test addition, subtraction, multiplication, and division, ensuring each method behaves as expected, even when we throw in some tricky cases, like division by 0. And that's how we're going to ensure our calculator is really reliable. As we begin to wrap this up, it's important to remember that writing tests is not just about checking if everything works. It's about making sure that as your codebase evolves, you can confidently make changes, knowing your tests will catch any regressions. Now, using Pytest has several advantages. It's super easy to set up, provides organized output, supports fixtures and parameterized tests, and integrates seamlessly with CI/CD pipelines. So, as you embark on your journey with Pytest, embrace the power of testing. Write tests that are clear and straightforward. Refactor your code with confidence. Just know that a well-structured suite of tests is there to catch those pesky issues before they become a problem. Happy testing! Effective testing is crucial for the success of any software project, especially when developing more complex systems. So, today we're going to dive deep into the intricacies of creating test strategies specifically for our project, the Cards project. Now, we've already learned that effective testing is fundamental in software development, and with Pytest in our toolkit, we're set up for success. It's super user-friendly. We've explored how to write test functions, organize them in files, and leverage features like fixtures and parameterization for efficient testing, right? Plus, we've discussed how to run those tests, interpret the results, and keep things maintainable, all while emphasizing the importance of clear assertions and feedback for seamless debugging. Our ultimate aim is to create a robust suite of tests that ensures our code remains reliable as it evolves. Now, let's shift gears and focus on how we can effectively develop test strategies that will not only streamline our testing process, but really enhance the reliability of our software. Now, let's dive into the Card Manager class, which is super central to our card registration functionality. This class features a method called Register Card, and guess what its job is? Yup, it's responsible for validating and registering a card using its number. So, when you're implementing this method, it's crucial to first check if that card number is valid by calling the isValidCardNumber method. Now, if the card number fails validation, the method will raise a value error. This way, we make sure that only appropriate inputs make their way through the registration process. Next up, we're going to implement the isValidCardNumber method. This handy function checks that the card number has exactly 16 digits and, importantly, only contains numerical characters. This simple validation step really helps keep our registration logic in line with the expected formats for card numbers, reducing the chances of errors popping up later on. By organizing our functionality inside a class structure with this clear separation of concerns, registration and validation, we're promoting better organization and readability within our code. And you know what? This structure ultimately makes it easier to test and maintain, paving the way for a more robust testing strategy as we start developing our tests in the future. Next, we're diving into writing some test cases using Pytest to verify how our card registration method works. Each test function here is going to check a specific scenario, making sure our application behaves just as we expect under different conditions. All right, let's kick things off with a test that successfully registers a valid card number. When our method gets a valid input, it should return a success message, right? Cool. Next up, we need to think about what could go wrong. So we're creating tests that simulate different erroneous scenarios. For example, what happens if the card number is too short? In that case, we expect a value error to pop up, underscoring the importance of proper input validation. It's crucial, right? Also, we have to account for non-digit characters because, let's face it, card numbers should only have digits. So we need to make sure that any improper format triggers the expected error. And let's not forget about those edge cases, like empty strings or strings that are just made of white space. Each of these tests confirms that our card manager responds appropriately to invalid inputs, which not only reinforces the robustness of our system, but also boosts our confidence in its performance across a range of inputs. Through this structured testing approach, we're really enhancing the reliability of our code. Awesome, right? Next, we will focus on how to structure our test files in a way that enhances maintainability and organization, particularly for the Cards project. You see, a well-defined directory structure not only makes it easier to locate your tests, but it also sets your project up perfectly for future expansion. Now, let's take a look at a proposed directory setup that we can implement. In this structure, the main project files will reside in the Cards folder, and right there we'll have the core functionality, like the card manager housed in card_manager.py. Meanwhile, to keep things neat, all related tests will be isolated within a tests directory. Inside this directory, we can create subfolders that align perfectly with the components of our project, specifically a test_cards folder for our card-related tests. This way, all test cases concerning card functionalities would be gathered in test_card-manager.py. Such a structure simplifies navigation and encourages clear organization, allowing anyone on your team, or you in the future, to quickly find and understand the relevant tests linked to specific parts of the codebase. Overall, this organization is not just about neatness, it's a strategic approach to effective testing and project scalability. Now, let's implement a fixture to streamline the creation of our card manager instance for our tests. We're going to define a fixture called card manager, which conveniently returns a new instance of card manager every time it's invoked in our test functions. This approach really helps us reduce repetitive setup code, making our tests more concise and focused on what they aim to validate rather than getting bogged down by initialization details. Next up, we'll write our test functions, each tailored to validate different scenarios about card registration. So, first we have test register valid card, which ensures that a valid card number gives us the expected success message. Following that, we'll tackle various invalid inputs. Think incorrect card number lengths, non-digit characters, empty strings, and even strings packed with just white space. Each of these tests uses the Pytest.raises context manager to confirm that the right value error is raised, complete with an appropriate message. By employing the structured approach with the fixture, we adhere to the dry principle, and hey, we also enhance the clarity of our tests. It allows us to focus more on the assertions rather than the setup, which really boosts test maintainability and readability. Next, we will implement parameterized tests using Pytest, which allows us to run a single test function with different sets of inputs. This feature is super handy for consolidating repetitive test scenarios into one concise function. In our example, we will use the @pytest.mark.parameterize decorator to define a list of tuples containing various card number values and their corresponding outcomes. We'll be testing both valid and invalid card numbers by checking if the cardmanager.registerCard method behaves as expected. For valid input, we expect a successful registration message, while invalid entries, like short lengths, non-digit characters, and empty spaces, should trigger a value error with a specific message. The assertions within the function will confirm that our logic holds true across different scenarios. This approach not only reduces redundancy in our test code, but also enhances readability and maintainability. By having all related test cases in one function, we ensure that our testing strategy is comprehensive and organized, covering multiple scenarios efficiently. Now, let's dive into building a straightforward payment processing system that fits seamlessly into our card registration workflow. We kick things off by defining a payment processor class. Inside this class, we create a method called process_payment, which handles all the payment operations. Now, here's the cool part. This method first checks if the payment amount is greater than 0. I mean, we only want valid transactions to go through, right? If the amount checks out, it gives you a nice confirmation message. But if it's not valid, watch out, it raises a value error. So next up, we're going to implement an integration test named Test Card Registration with Payment. This test is super important. Now let's dive into building a straightforward payment processing system that fits seamlessly into our card registration workflow. We kick things off by defining a payment processor class. Inside this class, we create a method called process_payment, which handles all the payment operations. Now, here's the cool part. This method first checks if the payment amount is greater than 0. I mean, we only want valid transactions to go through, right? If the amount checks out, it gives you a nice confirmation message. But if it's not valid, watch out, it raises a value error. So next up, we're going to implement an integration test named Test Card Registration with Payment. This test is super important because it verifies that the card registration and payment processes work together smoothly. First, we'll assert that a card can be registered successfully by calling the register card method from our card manager instance. And, of course, we check that it returns a success message. So meanwhile, we're going to instantiate our payment processor and check the payment process by making a payment of 100. If that goes well, it confirms that all our components are interacting just as we want them to. This really highlights the significance of integration testing in making sure different parts of our application are, playing nice together. Now, let's implement a continuous integration setup that will really help streamline our testing process. In this configuration, we're going to specify that our CI job gets triggered on events like code pushes and pull requests. What does that mean? Well, it ensures that every change we make to the codebase is automatically tested. So, how do we get started? First, we need to set up the environment to run our tests on the latest version of Ubuntu, which is super important. The steps we follow within this job include checking out the current code, setting up our Python environment with a specific version, and installing all the necessary dependencies for our project. This means upgrading pip and also installing Pytest. Next up, we're going to instruct the CI tool to run the test suite. Why? Because we want to make sure all tests are executed in a fresh environment every time there's a code change. This approach is fantastic because it not only verifies the quality of our code, but also catches errors early in the development lifecycle. Ultimately, this helps safeguard our main branch from potential issues. By integrating CI into our workflow, we enhance our development process and cultivate a culture of continuous improvement, making it an essential strategy for maintaining robust and reliable software. All right, let's jump into the next part. In conclusion, developing a test strategy for projects like the Cards project is absolutely essential for long-term success and maintainability. By prioritizing comprehensive coverage, organizing our test files effectively, utilizing fixtures, embracing parameterization, and integrating CI practices, we're laying down a solid foundation for a reliable codebase. And remember, testing isn't just about validating functionality. It's about crafting a safety net that empowers developers to iterate quickly and confidently. So let's keep refining our strategies and stick to those best practices in testing. Your future self and your team will definitely thank you for it. Now, as we continue pushing the boundaries of our projects, it's vital that we don't overlook the significance of a robust test strategy that will support us on this journey. Happy coding! Now, let's take a closer look at our card class, crafted to effectively manage task tracking data. We're harnessing Python's data class feature here, which, believe me, really simplifies attribute management for us by automatically generating those essential methods for initialization, comparison, and even representation. So, in this class, we define several key fields: summary, owner, state, and ID. And we're giving them sensible defaults. This means we can easily create card objects without the hassle. What's really cool is that we've included methods that let us convert a card instance to and from a dictionary format, making data serialization and deserialization a breeze. Next up, we're going to write a test function to ensure we can access those fields in the card class. This function will create an instance of card, assigning specific values, and then it'll check those values using assertions to make sure they're stored correctly. This is so important because it helps us catch any discrepancies quickly with Pytest, so we maintain the integrity of our class functionalities. Now, as we dive into crafting more test functions, we're going to explore various scenarios, like testing those default values, checking for equality, and, converting between formats. All of this is going to deepen our understanding of how the card behaves and ensure it's reliable in real-world applications. Now, let's implement a test function to verify the default values assigned to a new instance of our card class. When we create a card without specific attributes, we expect it to default to those predefined values we've set. The test function, named testDefaults, initializes a card object without any parameters and runs a series of assertions to confirm the default states of its attributes. So, specifically, it checks that summary and owner are set to none, that state is correctly defaulted to to-do, and that ID is also none. This focused and straightforward approach ensures that the class behaves as intended when instantiated without arguments. By maintaining clarity and purpose in our tests, we not only confirm functionality, but also create documentation that reflects the expected behavior of our class. As we enhance our card class further, this foundational check plays a crucial role in maintaining code reliability by guarding against unintended changes in default behavior. Now let's dive into implementing a test function to check the equality of two card objects. In this test, we'll create two instances of the card class, both initialized with the exact same attributes: a summary of do something, an owner named Alice, a state of to do, and an ID of 1. By using the equality operator, that's assert C1 equals C2, we can effectively verify that these two objects are considered equal based on their field values. And here's where it gets cool. Thanks to the data class decorator, Python effortlessly manages the comparison of all those specified fields. This not only cleans up our code, but also keeps our tests straightforward and super easy to understand. As a result, this test really bolsters our confidence in the correctness of our card class, allowing us to handle object equality smoothly as we build out even more features for our task tracking application. So, we're going to write a test function called testInequality. This function creates two card instances. Let's call them C1 and C2. Each of these cards has unique summaries, owners, states, and IDs. For instance, C1 represents a task assigned to Alice, while C2 represents a different task assigned to Bob. What we're doing is asserting that C1 is not equal to C2, which allows us to check if our equality logic is really functioning as it should. This test is super important because it validates that our implementation truly distinguishes card instances based on their properties. When objects have different attributes, they should definitely not be viewed as equal. This assertion captures that crucial principle. By ensuring this functionality, we're not just making accurate comparisons within our task tracking application, but we're also enhancing the reliability of our code overall. This helps us make sure that the underlying logic is solid and behaves as expected. And by carefully validating how our card objects respond in various scenarios, we're really strengthening the robustness of our software testing framework, a key takeaway for maintaining quality control in the cards project. Now, let's take a deep breath in. Look at how we can validate the process of creating a card instance from a dictionary, something that's pretty common in applications that serialize or deserialize objects. We're going to whip up a test function called test_from_dict. First up, we'll create a card instance. Let's call it C1, right? We'll give it some specific attributes like summary, owner, state, and ID. Now, we also need to define a dictionary. Let's name it C2dict, which will mirror these attributes, but in key value pairs. Pretty straightforward, right? Next, using the fromDict class method, we'll create a new card instance. We'll call it C2, utilizing that dictionary we just made. Now here's the kicker. This test is all about asserting that C1 and C2 are equivalent once they're initialized. That means we're confirming that the conversion from our dictionary to the card object accurately reflects everything we intended. Testing these conversions is crucial. It not only ensures that our data integrity stays intact while we're jumping between different formats, but it also lays a solid foundation for handling data serialization and deserialization as our applications evolve. And you know, this practice, it really highlights the importance of crafting reliable functionality in our software, making sure that our classes work as expected in all kinds of scenarios. So, let's keep that in mind as we dive deeper into our coding journey. Let's dive into writing a test function to ensure our card object can be converted back into its dictionary representation using the toDict method. This is super important for maintaining data integrity in our task tracking system, as it helps us verify that all the attributes are accurately represented in the dictionary format. So here's how we do it. We'll first create an instance of the card with some specific parameters, like summary, owner, state, and an identifier. Once we have that, we invoke the toDict method on our card instance, which should give us a dictionary that contains those same values we just set up. Deep breath in. Next, we'll define what our expected dictionary looks like. This should mirror the attributes of our card exactly. Finally, we assert that the output from the toDict method matches our expected dictionary format. This step is really crucial because it makes sure that as we work with our data, whether we're displaying it or manipulating it, it sticks to a consistent structure. This enhances reliability and maintainability as our application evolves. By implementing this test, we're really reinforcing our commitment to quality and accuracy in the software we're building. Next, we're going to create a test function to handle situations where something doesn't go quite right, like when a critical parameter goes missing. We'll focus on the cards.db class, which really needs a file path to run smoothly. So we want to make sure that if this important piece is absent, it raises the right kind of exception. To do this, we're going to tap into Pytest's raises function, which is super handy for checking if specific exceptions pop up when we expect them to. All right, let's kick things off by crafting a test function called test_no_path_raises. Inside this function, we're going to use a context manager to wrap the instantiation of the cards.db class. This will help us catch any exceptions that get thrown. Now, by stating type error within pytest.raises, we can accurately assert that this exception is thrown when there's no path provided. This approach not only ensures our code reacts appropriately to improper input, but also protects us against any future changes that might mess with how exceptions are handled. Yep, it reinforces our test suite's reliability and maintainability. Now, let's dive into implementing our test cases in a structured way by grouping them into a test class. We're going to organize our related tests under a single class called TestCard, which not only makes things clearer, but also boosts the maintainability of our testing suite. Each method inside this class represents an individual test, corresponding to the different functionalities we've explored with the card class. As we define these methods, we'll be including tests for field access, default values, equality, inequality, and those handy conversion methods like fromDict and toDict. Each method will have assertions that check whether the card class behaves as expected in various scenarios. For example, our test field access method will ensure that fields such as summary, owner, state, and ID are accessible and set correctly once we create an instance. Meanwhile, test defaults will verify that if a card is initialized without any parameters, it defaults to the appropriate values. Pretty neat, right? By grouping our tests this way, we can run all related tests together seamlessly, which definitely enhances our testing process as it scales up. This organizational strategy not only helps reduce the complexity of testing multiple aspects of our class at once, but also guarantees that we've got comprehensive coverage of its functionality. Now, let's dive into running specific subsets of tests using Pytest. By making use of the K flag, we can zoom in on particular test classes or methods without needing to run the entire suite. This is especially handy when we're dealing with a large number of test cases. So, for example, if we want to execute just the tests related to the test card class, we would use the command pytest-k testcard. What this does is instruct Pytest to filter and run only those tests that belong to the specified class. It really helps us streamline the testing process and focus on areas of the code that need our attention. The ability to run tests selectively is a game changer because it allows us to easily verify functionality associated with specific features. This not only enhances our productivity, but also boosts our efficiency as we develop and maintain our software. Oh, isn't that neat? In conclusion, writing effective test functions in Pytest is all about having a systematic approach. By utilizing the assert keyword, structuring our tests with helper functions, and tapping into exception testing, we can really ensure our code stays reliable and robust. Now, moving forward, one thing to keep in mind is documenting your tests well. Each test is like a piece of documentation that explains how your code behaves under various conditions, right? Not only does this help with maintenance, but it also gives new developers a solid roadmap to understand the ins and outs of your application. So, thank you for joining me today. I really hope you're feeling inspired to dive in and start writing tests for your own applications. Happy testing! Organizing tests into classes is a super powerful strategy that really enhances the structure, the readability, and maintainability of your test code. When you've got multiple related tests, grouping them together keeps everything nice and tidy, and, more importantly, provides better context for what they're all about. So far, we've learned that effective testing, especially in Python using Pytest, is essential for developing reliable and maintainable software, particularly for that cards project we're working on. We've explored the significance of writing test functions to verify code behavior, covering fundamental aspects like field access, default values, equality checks, and conversion methods. And we really emphasized grouping those tests into classes and utilizing Pytest's features to streamline our testing process. Moving forward, our goal is to implement these strategies to ensure we're practicing robust testing in our applications. Now, let's dive into implementing our card class and setting up some exciting tests for it. First off, we're going to define the card class using the data class decorator. This nifty little tool helps us create classes that mainly focus on storing data. Inside this class, we include attributes like summary, owner, state, and ID, each with their default values already set. Now, to make our lives easier, we're also defining two methods that will help us convert instances to and from dictionaries and card objects. This means we can easily serialize and deserialize, which is super handy. Next, we're creating our test class, test card, that'll handle all the tests related to the card class. In this class, the setup class method is key because it initializes two card instances we'll use across our tests. This approach really cuts down on redundancy. Great time saver. After that, we've got a teardown class method for any cleanup we need to do after our tests run. As for the test methods, they're focusing on the various functionalities we want to check. For instance, test field access tests that the attributes of our card objects return the expected values, making sure our constructor's doing its job right. Meanwhile, test defaults ensures that a card instance created without any parameters gives us the correct default values. Which is really important. With this organizational structure, our tests become not just manageable, but also, really clarify the expected behaviors of the card class. It keeps everything running smoothly, and that's what we want. Next, we're diving into a fun little test method that helps us check if two instances of the card class are equal. This method is cleverly named test equality, and its main goal is to ensure that when we have two card objects with the same attributes, they're treated as equal. So how do we do this? Well, we use assertions to compare our first card instance, card1, which we set up in the setup class method, with another newly created card object that has exactly the same attributes. But that's not all. We also make sure to test that card1 is not equal to card2, which has different attributes. This step is super important because it really reinforces the integrity of our equality implementation in the card class. It's all about making sure our equality logic holds up in different scenarios. Now, by adding this test to the test card class, we're enhancing our test suite's cohesiveness. It makes it crystal clear that these tests specifically focus on how card objects behave when it comes to equality. This is a great boost for readability and maintenance of our code. Plus, as we evolve our card class, we can quickly verify that the core functionality surrounding equality remains effective and reliable. Next, let's dive into adding tests for converting a card instance to a dictionary and vice versa. First up, we have the test_from_dict function. This nifty little test helps us ensure that a dictionary representation of a card can be turned back into a card object seamlessly. So, it starts by creating a dictionary filled with predefined card attributes, right? Then, it makes use of the fromDict class method to cook up a brand new card instance. And here's a fun part. An assertion is used to check that this shiny new instance matches an existing card object. It's like making sure everything is in place and functioning as it should. Now, let's switch gears a bit and take a look at the test_to_dict method. This one checks whether turning a card instance into a dictionary actually gives us what we expect. So, it calls toDict on a card instance and then compares that result with an anticipated dictionary that outlines all of the card's attributes. Pretty straightforward, right? Now, both of these tests are absolutely essential for making sure our conversion processes tick perfectly, ensuring that our card class behaves just like we want when it comes to translating to and from its dictionary representation. By keeping these tests neatly contained within the same test card class, we promote clarity and simplicity, making it super easy for future developers to associate these tests with the conversions they're validating. Now, let's implement a fixture that enhances the efficiency of our tests by scoping it to the test class. The card fixture we define will create an instance of the card class only once for all tests within the test card with fixture class, which is super handy since it minimizes redundant object creation, right? This is especially beneficial when dealing with resources that are costly to initialize or if you want to keep a shared state across multiple tests. So, in our test card with fixture class, we have two test methods. The first one, test card summary, checks if the summary of the card instance created by the fixture matches the expected value, which is do something. Then we have the second method, test card owner, verifying that the card's owner is Alice. By using the fixture, both tests can efficiently tap into the same card instance. Pretty neat, huh? This really shows the advantages of organizing our tests this way. Overall, this approach not only clarifies the relationship between the tests and the fixtures, but also illustrates how to effectively reuse setup code. It makes our tests cleaner and way more maintainable as we keep evolving our testing strategy in the cards project. Now, let's dive into how to structure our tests by introducing base test classes. This really helps streamline shared functionalities across multiple test cases. We'll kick things off with the base test card class, and here's where it gets interesting. It includes a setup class method that initializes a default card object. This base class is a real time saver. It lets us avoid redundancy, allowing any derived test classes to access the same setup logic without having to redefine it. Next up, we'll implement a specific test class called test card default, which is going to inherit from base test card. In this derived class, we define a test method named test_default_card. Here, we're leveraging the card default instance initialized in our base class to assert that its state is to-do and its owner is default owner. By using inheritance like this, we can focus on writing our test cases without all that repetitive setup, making our code way more maintainable over time. This approach really embodies best practices in our testing framework, enabling us to organize our tests in a scalable and efficient way, especially as our test suite grows. So, to sum it all up, using base test classes allows us to group related functionalities neatly and supports clear and concise test definitions. You know how teams often grow and new developers come on board, right? Well, a clean, organized set of tests makes onboarding a breeze. Future developers can quickly grasp the intent behind your code, and as they look through your tests, they'll appreciate how you've structured everything into these cohesive units. And it gets better. When you combine this with continuous integration practices, organized testing in classes really helps facilitate the debugging process. If a test fails, developers know exactly where to look. No more sifting through a mountain of unrelated tests. How efficient is that? Addressing failures can happen quickly when you gather all relevant tests with clear relationships to the code you're testing. This brings so much efficiency to your workflow. Now, let's dive into running our organized tests using Pytest. To kick things off, we just need to use the Pytest command followed by the name of our test file. This is where Pytest's auto-discovery feature comes into play, and it's pretty smart. When you call Pytest-Card.Py, it'll automatically look for any classes or functions that fit its test patterns. Yup, including everything we set up in our test card class earlier. Now, if you want to get a bit more insight into the nitty-gritty of how your tests are running, try using the -v flag. This enables verbose output, which means Pytest will provide a clearer picture of which tests passed or failed, along with some detailed logs about any issues it found. Trust me, this feedback loop is pure gold for debugging and improving your code, as it leads you directly to what needs your attention. So, with just a little effort, you can efficiently run and analyze the results of your organized tests, totally boosting your development workflow. To wrap it all up, organizing your tests into classes creates a structured, readable, and maintainable testing suite. By grouping related tests together, using class-level setup methods, and leveraging those shared fixtures, you really enhance collaboration and improve efficiency. It's like creating a robust testing framework for your applications. When you implement these best practices, not only will your current code be well tested, but you'll also be laying a solid groundwork for any future development. So happy testing out there, and enjoy refining your Pytest skills.
Now that you've used Pytest to write and run test functions, let's turn our attention to test helper functions called Fixtures, which are essential to structuring test code for almost any non-trivial software system. So far, we learned that organizing tests into classes significantly improves the structure and readability of test code, making it more maintainable and efficient. We discussed the use of class-level setup and teardown methods, which eliminate redundancy and enhance clarity. Additionally, we highlighted the importance of shared fixtures and base test classes to facilitate collaboration and simplify onboarding for new team members. Implementing these strategies will bolster our testing practices and support future development efforts. In this lesson, we will cover what fixtures are, how to create them, and their various use cases to help make our testing code cleaner and more efficient. Now let's implement a fixture to manage a database connection for our tests. We begin by importing the Pytest library, which contains the necessary functionalities to create and utilize fixtures. The @Pytest fixture decorator precedes our DB connection function, indicating to Pytest that this specific function will act as a fixture. Inside the function, we simulate establishing a connection to the database by creating a variable named connection and assigning it a string that indicates the connection is established. The yield statement plays a crucial role here. It allows the fixture to pass the connection variable to any test function that requires it. This is where the actual testing occurs. After the test completes, the code following the yield statement is executed, which serves as a teardown process. In this case, we set the connection to none and print a message stating that the database connection has been closed. This structured approach ensures that resources are properly managed and cleaned up after the tests are conducted, promoting reliability and maintainability in our testing practices. Now let's see how we can implement a simple test function using our DB connection fixture. The test query function is designed to validate if our fixture works correctly by asserting that the established database connection meets our expectations. In this case, it checks if the DB connection equals the string database connection established. This assertion helps ensure that the fixture has successfully set up the connection before the test runs, reinforcing the idea that Pytest automatically handles the execution of the fixture. With this configuration, whenever we call test query, Pytest will first invoke the DB connection fixture, providing a clean and reliable setup for our test function. This clear separation of test logic from setup details enhances the maintainability of our testing strategy. It allows us to focus solely on the primary goals of our tests, while the fixture takes care of preparing necessary resources, ensuring each test runs with a consistent environment. By adopting this approach, our tests become more succinct, organized, and adaptable to changes in the database connection logic in the future. Now let's see how we can modify our DB connection fixture to accept parameters, allowing us to test different scenarios more efficiently. By adding the params argument with the values test, production, we instruct Pytest to execute any tests that depend on the DB connection fixture for each parameter specified. This means our tests will run twice, once for each environment, which provides us with valuable insights into how our code behaves under different configurations. Within the fixture, we leverage the request argument to access the current parameter in use. As the fixture is executed, it constructs a connection message that reflects the specific environment being tested, either test or production. The yield statement sends the connection string to the test function, while the code following the yield ensures proper cleanup by indicating when the connection is closed for that particular environment. This approach not only reduces code duplication, but also enhances the robustness of our testing, as we can efficiently validate our functionality across varied settings with minimal effort. Now we'll see how we can implement our parameterized fixture within a test function. The test-env-query function leverages the DB connection fixture that we set up earlier, which is configured to accept parameters for different environments, specifically test and production. This allows the test function to be executed twice, once for each of these specified environments. In this function, we assert that the string database connection established is present in the output from the fixture. By using parameterized fixtures, you can ensure that your tests are adaptable to multiple scenarios without duplicating your setup code. This technique significantly enhances the robustness of your testing approach because it verifies that the connection setup works consistently across different environments. After executing this test, you'll see output in the console that confirms whether the connection was successfully established for both the test and production environments. Additionally, the cleanup code, which ensures proper closure of the database connection, runs as well for both scenarios, showcasing how parameterized fixtures can make testing cleaner and more efficient. Now let's implement a fixture for a mock web service, which illustrates the use of Pytest fixtures to simulate external dependencies. We define a fixture named mock service that provides a base URL for a mock web service, allowing our tests to interact with this simulated endpoint. Using the @Pytest fixture decorator, we indicate to Pytest that this function can be utilized as a fixture. Within the mock service fixture, we establish a variable base URL that holds the mock service's URL. The yield statement is crucial because it provides the base URL to any test function requiring it. After the test completes, the code following the yield executes as cleanup, ensuring any resources related to the mock service are cleared. Next, we will write a test function called test_service_call that utilizes the mock service fixture. In this test, we make a GET request to the mock service URL and assert that the response status code is 200, indicating a successful interaction. This structure emphasizes the clarity of testing outcomes while hiding the complexity of the setup behind the fixture, enabling a focus on the result of the service call instead. Now let's see how we can implement a fixture that operates at the class scope. In this example, we define a fixture called DB_connection class, using the @Pytest fixture decorator with an argument specifying its scope as class. This means that the fixture will only create a single instance of the connection variable for all tests within that test class, which helps in reducing setup time by avoiding redundant connections for each test. Inside the fixture, we simulate establishing a database connection by assigning a string indicating the connection to the connection variable. The yield statement is crucial here. It delivers the established connection to any test function that requests it. After the tests are run, the code following the yield statement executes, providing cleanup logic in this case, a print statement that notifies when the database connection is closed. By leveraging class-scoped fixtures, we enhance our testing efficiency by reusing resources across multiple tests while ensuring that resources are properly managed, which is particularly beneficial in scenarios when numerous tests share the same dependencies. Now let's take a look at how we can implement nested fixtures in Pytest. In this example, we define two fixtures, user and authUser. The user fixture returns a dictionary containing a username, which creates a simple user object. This encapsulated setup allows for reusable code that can be easily modified. Next, we introduce the authUser fixture, which takes the user fixture as a parameter. This means that when authUser is invoked, it first calls the user fixture, modifies the user data by adding an authenticated key set to true, and then returns the updated user object. The beauty of nesting fixtures is that it allows you to create comprehensive setups where one fixture builds on another. This is particularly useful in testing scenarios where multiple layers of dependencies are required. By using nested fixtures, your tests can remain concise and focused, ensuring that the setup logic is clear and easily maintainable. In our example, this approach helps streamline testing by producing a properly configured user object ready for assertions, simplifying the testing process for user authentication scenarios. Now let's see how we can implement a test function that utilizes our nested fixture. The test_authenticated_user function is a practical example of leveraging the authUser fixture. This fixture provides a dictionary representing a user, complete with an authentication status and a username. When test_authenticated_user is called, Pytest automatically recognizes that it needs to resolve the authUser fixture first. The authUser fixture, in turn, depends on the user fixture, which means that when it is executed, it creates a user dictionary and modifies it to include an authenticated key. As a result, the test function receives a fully populated user dictionary, allowing us to perform assertions directly. The first assertion confirms that the user is authenticated, ensuring that the authenticated property is set to true. Following that, the second assertion checks the username to verify that it matches the expected value of test user. This demonstrates the effectiveness of nested fixtures, showing how they facilitate complex setups while keeping test code clean and focused on the logic being tested. In summary, fixtures are powerful components that help you with the setup and teardown of resources needed for your tests. They allow for code reuse, provide multiple parameterized scenarios, and enhance the organization of your test suite. By using fixture scopes appropriately, you can tailor the lifetime of your test resources to optimize performance and clarity, ensuring more efficient testing. If you haven't yet started using fixtures in your own tests, now is a great time to incorporate them. You'll find that as your test suite grows, fixtures will simplify your workflow and help maintain focus on writing great tests. Going forward, keep exploring the full potential of Pytest, and remember to utilize fixtures wherever they can make your testing. Let's dive into the advanced usage of fixtures in Pytest, particularly focusing on fixture scoping, something that can really elevate your testing game. You might be wondering how you can leverage these powerful tools to create even more maintainable and efficient test suites. In this lesson, we're going to build on what we've learned so far about Pytest fixtures, especially parameterized and nested fixtures, as we explore their advanced features. So far, we learned that Pytest fixtures are essential for organizing test setups and teardowns, enabling code reuse and enhancing test clarity. We explored how to create basic and parameterized fixtures, which allow for testing different scenarios without duplicating setup code. Additionally, we discussed nested fixtures, which enable more complex test setups by allowing one fixture to depend on another. Understanding and leveraging fixtures is crucial for maintaining readable and maintainable test code as your test suite grows. Now we will talk about advanced fixture usage and scoping, which will give you even more flexibility in how you manage your tests. Now let's examine a function-scoped fixture in Pytest, which creates a new resource every time a test function requests it. The SumResource fixture demonstrates this by defining a resource that contains the string resource created. When a test calls this fixture, it yields the resource, meaning that the resource is set up for the test. After the test finishes executing, a cleanup step is run, indicated by the printed message, resource released. Next, we will see how this fixture is used within two test functions, test function 1 and test function 2. Both tests will assert that the value of the resource equals resource created. Importantly, since this is a function-scoped fixture, each test will receive its own instance of SumResource. This illustrates how using function-scoped fixtures is beneficial for ensuring isolation between tests, as changes in one test do not affect another. In situations where resources are more complex or costly to create, we might consider using other scopes like class or module to enhance efficiency and reduce overhead from repeated setup. Now let's take a look at a class-scoped fixture designed to instantiate a shared resource for tests within a specific test class. By defining a fixture with scope equals class, you ensure that the resource is created only once for all tests encapsulated in that class. This approach significantly optimizes resource usage, especially for expensive setups. Next, we implement the fixture which yields a shared resource message and prints a confirmation upon its release. This means both tests within the class, test1 and test2, will access the same instance of the shared resource. Consequently, you'll observe that when both tests complete, the release message is displayed only once, highlighting the efficiency of this scoping method. This design pattern promotes better performance and resource management, as it avoids redundant setups for tests that can safely share the same context. Therefore, when organizing tests that benefit from sharing state or context, using a class-scoped fixture is an effective strategy, ensuring clarity and maintainability within your test suite. Now let's implement a session-scoped fixture in Pytest. This is particularly useful for scenarios where an expensive resource needs to be set up only once for the entire testing session. In our example, we define a fixture named expensive resource. It is marked with the @Pytest fixture decorator, specifying the scope as session. This tells Pytest to create the resource just once at the start of the test run and only clean it up after all tests have completed. Inside this fixture, we initialize the resource with a string indicating it has been initialized. We use the yield statement to provide the resource to any test that requires it. After the tests finish running, the code following the yield will execute, which in this case prints a message confirming that the expensive resource has been cleaned up. Next, we'll see how multiple tests can utilize this fixture. In the test functions, testExpensive1 and testExpensive2, we assert that the provided resource equals our initialized string. This setup allows both tests to share the same instance of expensive resource, demonstrating the efficiency and convenience of using session-scoped fixtures to minimize redundant setup time. Now let's implement a parameterized fixture that will allow us to test our code with multiple sets of data efficiently. The code defines a fixture named parameterization, which uses the @Pytest fixture decorator to specify a list of parameters, case 1, case 2, and case 3. Each time a test function requests this fixture, it will receive a different value from the params list, allowing for different configurations in the tests. Next, we will write a test function called test_parameterize that utilizes the parameterization fixture. In this function, we assert that the string returned from the parameterization starts with resource4. This assertion tests the output based on the parameter passed in each execution of the test, ensuring that our code behaves correctly for various cases without duplicating the test logic. By running this test, Pytest will automatically execute it 3 times, 1 for each parameter. This approach not only streamlines our testing process by reducing redundancy, but also enhances our ability to validate the code against diverse inputs efficiently. Now let's see how we can implement a parameterized fixture to handle different user roles in our API tests. Here, we define a fixture called role-based resource that is parameterized with 3 different roles: admin, user, and guest. By using the params argument, Pytest automatically runs any test that utilizes this fixture 3 times, once for each role. Within the fixture, we yield a string that represents the resource associated with the current role being tested. Next, we will write a test function named test_role_access that consumes this fixture. As the test runs, it retrieves the role from the role-based resource yield value. Depending on the role, the test performs different assertions. For the admin and user roles, we assert that access is granted, while for the guest role, we assert that access is denied. This approach not only keeps our test code clean and maintainable, but also verifies the functionality across multiple scenarios without duplication, showcasing the power of parameterized fixtures in Pytest. Now let's implement nested fixtures to manage complex relationships between resources efficiently. The database connection fixture is defined with a module scope, meaning it will be created once per module and shared among tests, establishing a single database connection during that time. This is particularly useful for minimizing the overhead of repeated setup operations, like opening and closing a database connection. Next, we define the userData fixture, which depends on database connection. This setup allows you to create userData that leverages the database connection previously established. By yielding a dictionary containing user details, we're able to utilize this data in tests while maintaining a clear connection to the database setup. In the test user creation function, we access the userData fixture. This means our assertions can directly check the user credentials while ensuring they integrate smoothly with the underlying database connection. This organized structure enhances both the setup and tear-down processes, granting us greater control and clarity over the testing architecture. By using nested fixtures, we ensure our tests are tightly focused, efficient, and easy to maintain. As we've seen, advanced fixture usage and varying scopes in Pytest provide a plethora of options to optimize your tests. You can design your tests to be flexible, maintainable, and efficient through careful structuring of which fixtures to utilize based on contextual needs. Leveraging scopes like class and session not only reduces setup overhead, but also fosters better collaboration, as tests become easier to understand. Integrating parameterized fixtures, especially with real-world scenarios, allows you to ensure comprehensive test coverage without resorting to repetitive code. Each instance of running these fixtures brings invaluable insights into how your code interacts with various states and inputs. Finally, I encourage you to practice combining these advanced features as you continue building out your testing suite. Challenge yourself by designing tests that not only cover functionality, but also edge cases and integration scenarios relevant to your application. With these skills, you'll elevate not just your testing, but the quality of your code overall, leading to fewer bugs and a more resilient product. So go ahead, experiment with these techniques. In today's session, we are diving into the world of built-in fixtures in Pytest. These fixtures are one of the key components that can simplify your testing in Python, eliminating repetitive code and enhancing readability. So far, we covered the benefits of using Pytest fixtures, including how they aid in structuring test setups and enable code reusability. We explored fixture scopes, parameterized fixtures, and how to combine nested fixtures for complex setups. Now we will focus on the built-in fixtures that Pytest readily provides. Fixtures you can leverage right away without crafting them from scratch. Now let's see how we can implement the TMP path fixture in our tests. The code defines a test function named test_tmp_path, which accepts tmp path as an argument. This fixture automatically provides a unique temporary directory for each test run, eliminating the need for manual cleanup. Within the function, we create a temporary file named tempfile.txt in the tmp path directory. This is achieved by constructing a path using the division operator, which is a convenient way to define file paths in Python. We then write the string hello Pytest into this file using the writeText method. Next, it's crucial to verify that the content we've written to the file is correct. To do this, we utilize the readText method, which reads the content of tempfile.txt, and we employ an assertion to ensure that it matches the original string. The beauty of using tmp path is that once the test completes, the temporary file and its directory are automatically cleaned up, maintaining a tidy testing environment and avoiding any clutter in our file system. Now let's take a look at how we can utilize tmp path factory to manage temporary directories across multiple test functions during a Pytest session. In this example, we start by defining a test function that accepts tmp path factory as an argument, allowing us to create temporary directories with session-wide scope. We call the mktemp method on tmp path factory, specifying a name for our new temporary directory, which ensures that it is distinct and easily identifiable. This directory will serve as a parent for any temporary files we want to create during our tests. Next, we create a temporary file called anotherfile.txt within this newly created subdirectory. The code demonstrates writing some test content into that file, showcasing how we can easily manipulate files located in our session-wide temporary directory. Finally, we assert that what we wrote into the temporary file matches our expectations, confirming that the file operations functioned correctly. This use of tmp path factory not only maintains cleanliness in our file system, but also enhances testing flexibility by allowing data sharing between tests if necessary. Now let's see how we can implement the capses fixture to capture output during our tests. In this example, we define a test function called testOutput, with capses as a parameter that enables us to capture any output sent to standard output and standard error. Within the function, we print a simple message. This is a test output. This action would typically display the message on the console. However, by using capses, we can capture this output instead. After the print statement, we call the capses readoutAya method, which retrieves the captured output and stores it in a variable named captured. This captured object contains both out for standard output and for standard error. Next, we focus on asserting that the captured output matches our expectations. We access the out attribute of the captured object and strip any leading or trailing whitespace, then compare it to our expected string. If the assertion holds true, it confirms that the output produced by our print statement is correct, thereby validating the functionality of the code under test. This approach demonstrates how capturing standard output can enhance our testing process by allowing verification of printed messages or logs. Now let's see how we can implement environment variable manipulation in our tests using the Monkeypatch fixture. The code begins by importing the os module, which allows us to interact with the operating system's environment variables. We define a test function named testMonkeypatch, which accepts Monkeypatch as an argument, a built-in fixture provided by Pytest specifically for this purpose. Inside the function, we use Monkeypatch setenv to set an environment variable called testenv to the value 12,345. This step is crucial as it simulates how our application would behave when this variable is present in the environment. The magic of Monkeypatch is that after our test function finishes executing, the original value of testenv is automatically restored, ensuring that we don't leave any side effects on the system. Finally, we assert that the value of testenv retrieved using OS getenv equals 12,345. This assertion verifies that the environment variable was successfully patched and our application reads it as intended. This method allows for isolated testing without altering the real environment permanently, making it a robust technique for controlling external factors during testing. Now let's implement a test for a function that reads data from a file while utilizing the Monkeypatch fixture to avoid any actual file interactions. We begin by defining a function, readDataFromFile, which attempts to open and read a file named data.txt. This function will need to be tested, but during our testing, we want to simulate this file reading without relying on an actual file. Next, we'll set up a test function called testReadData, where we will use Monkeypatch to replace the built-in open function. Within this test, we define a mock version of the open function named mockOpen, which will return a predetermined string, mocked data, instead of reading from the file. By using Monkeypatch setData, we dynamically replace the original open function with our mockOpen for the duration of the test. Finally, we assert that calling readDataFromFile yields the expected string, mocked data. This approach effectively isolates the logic of our function from actual file operations, allowing us to test its behavior without side effects and ensuring that our tests are fast and reliable. Now let's take a look at how we can verify log messages using the caplog fixture in our tests. In this code, we begin by importing the logging module and creating a logger instance named testLogger. This logger will be used to emit log messages for our test. First, we log an informational message to demonstrate basic logging functionality. Next, the power of caplog comes into play as we utilize it to capture log messages. By entering a context manager with caplog at level logging info, we ensure that any log statements made within this block at the info level are captured. We then log another message to illustrate how caplog records it. Finally, we assert that the expected log message appears in the captured log output. This verification step is crucial, as it confirms that our application is logging as intended and helps maintain the integrity of logging practices throughout our code. Using caplog, we can seamlessly audit application behavior during testing, ensuring robust and reliable logging functionality. As you can see, these built-in fixtures greatly enhance your capability to write clean and effective tests in Pytest. Each fixture provides a unique mechanism that can be applied based on what your test case demands. Whether you need temporary directories, output capturing, environment modifications, or logging verification, Pytest has you covered right out of the box. So, before we wrap up, remember that depending on your testing needs, you'll often find yourself reaching for these built-in fixtures rather than recreating similar functionality from scratch. Once you start integrating these fixtures into your testing practice, you'll find that they not only save you time, but also make your code cleaner and easier to understand. Looking ahead, we'll explore some of the other built-in fixtures that Pytest offers, such as cache for managing data across multiple runs and Pytest-Config to access configuration values directly. Each of these will further empower you to create efficient tests tailored to your projects. So make sure to stay tuned as we continue to dissect the excellent capabilities Pytest has in. Now let's take a look at how we can implement a function to fetch user profiles from an external API while avoiding real network calls during testing. We start by defining a function called fetchUserProfile, which takes a user ID as an argument. This function constructs a URL to make a GET request to the specified API endpoint using the requestGet method. Once the response is received, it extracts the user data by calling the JSON method on the response object, which is expected to return the user details in JSON format. Next, we will write a test function named testFetchUserProfile, which uses the Monkeypatch fixture from Pytest. This test will simulate the API behavior by creating a mock version of the requestGet method. Inside the test, we define a function called mockGet, which returns a mock response class that includes a JSON method returning predefined user data. By using Monkeypatch setAtta, we temporarily replace the original requestGet with our mock for the duration of the test. This allows us to validate that the fetchUserProfile function correctly handles the mock response without making an actual HTTP request, ensuring our tests run quickly and consistently. Lastly, we assert that the returned user profile matches the expected values, confirming the function works as intended. Next, we will write a function to retrieve the database URL from the environment variable DatabaseURL. This function, getDatabaseURL, utilizes the OS getEnv method to fetch the value, defaulting to an in-memory SQLite database if the variable is not set. This flexibility allows our application to adapt to different environments based on the specified variable. Now, to test the behavior of getDatabaseURL, we will implement a test case using the Monkeypatch fixture. This enables us to temporarily modify the environment variable for the scope of the test without affecting the actual environment. In the test function, we use Monkeypatch setEnv to set DatabaseURL to a PostgreSQL connection string. When we call getDatabaseURL within this test, it retrieves the mocked value of the database URL. Finally, we assert that the returned value matches our expected input, confirming that the function behaves correctly under the altered environment. This approach ensures our tests remain isolated and clean, restoring the original state of the environment variable once the test concludes. Now let's take a look at how we can implement a notification system using the email service class. In this example, we define an email service class with a method, sendEmail, which simulates the action of sending an email to a recipient. The notifyUser function utilizes this service to send a welcome email to a specified user. Next, we will write the corresponding test using Monkeypatching. In the test notifyUser function, we create a mock email service class that overrides the sendEmail method. Instead of actually sending an email, we include assertions to verify that the correct parameters are being passed: the recipient's email address, the subject, and the body of the email. This approach allows us to test the notifyUser function without triggering any real email notifications. To achieve this, we use the Monkeypatch setAtta function to replace the email service class with our mock email service. Within this testing context, when the notifyUser function is called, it utilizes the mocked version of the email service, allowing us to effectively validate that our notification logic is functioning as intended without any side effect. Now let's take a look at how we can use Monkeypatching to modify behavior of built-in functions during testing. In this example, we have a function, getRandomNumber, which utilizes random to return a random integer between 1 and 100. However, for testing purposes, we want to eliminate randomness to allow for consistent, predictable results. To achieve this, we define a mock function, mockRandom, which always returns the same value, 42. Next, we utilize the Monkeypatch setAtta method to temporarily replace the original random function with our mockRandom function. This is done within the test-getRandomNumber test function. When we call getRandomNumber during the test, it now executes the mocked version, ensuring that it consistently returns 42. This enables us to make reliable assertions about the output of getRandomNumber, regardless of the inherent unpredictability of random number generation. By using Monkeypatching in this way, we've created a controlled testing environment that simplifies our assertions and improves test reliability. While Monkeypatching can be incredibly powerful, it's important to use it judiciously. Relying on Monkeypatching too heavily can lead to overly complex tests that are hard to read and maintain. It's generally recommended to use Monkeypatching for isolating dependencies and behaviors that are difficult or impractical to replicate in your tests without it. With that said, let's discuss best practices for using Monkeypatch effectively. First, ensure that what you're patching is necessary for the test. If you find yourself frequently needing to replace a piece of code, consider whether that code is overly complex or if it could be refactored to be more testable. Second, you should maintain clarity in your tests. Your intent should be clear. Anyone reading your test code should easily understand what is being patched and why. Adding descriptive comments can further aid in understanding the purpose behind each monkeypatching statement. Additionally, remember that monkeypatching is temporary. It only affects the scope of the test and is rolled back afterward, so be aware of any side effects that a patch could have on other tests in the same test file. Properly isolating changes is key to avoiding test failures that appear non-deterministic. Finally, as your skills with monkeypatching develop, you'll start noticing scenarios where its application can help simplify complex tests. With practice, you'll become adept at recognizing patterns that benefit from monkeypatching, leading to cleaner, more robust test suites. Now, you have a solid understanding of monkeypatching and how to apply it effectively in your tests using Pytest. Remember, it's all about creating a controlled environment for your tests, allowing you to isolate code behavior and execute precise validations. Whether modifying method behavior, changing return values, or adjusting environment variables, monkeypatching becomes a valuable asset in your testing toolbox. Now go ahead and apply what you've learned, and let's dive into the exciting world of parameterize in Pytest. We are now shifting gears to explore an essential feature that enables us to write cleaner and more efficient tests. So far, we learned about the Monkeypatch built-in fixture in Pytest, which allows for modifying code during tests without altering production code. We explored its applications, including simulating API responses, adjusting environment variables, and mocking classes or methods, which are crucial for efficient and isolated testing. Through various examples, we demonstrated how to effectively use monkeypatching to control the behavior of functions and ensure consistent test results. Now, we will cover the concept of parameterize and see how it can turn a single test function into many test cases, thereby enhancing our testing framework. Let's get started. Parameterize is a powerful tool in Pytest that enables you to efficiently run multiple test cases with a single function definition. By allowing you to pass in different parameters, it alleviates the need for repetitive test functions, offering cleaner and more organized code. Now let's see how we can implement our test scenarios using separate functions for each state of a code in our task management application. In this code, we define 3 distinct test functions: test finish from in prog, test finish from done, and test finish from to do. Each function tests the behavior of the system when a code with a specific initial state is transitioned to done. In test finish from in prog, we add a code with the state in prog to the database, invoke the finish method, and then retrieve the code to assert that its state has changed to done. Similarly, test finish from done tests that a code already in the done state remains unchanged when the finish method is called again, verifying that no unintended behavior occurs. The last function, test finish from to do, adds a code in the to do state and ensures, after calling finish, that it correctly transitions to done. While these isolated tests successfully cover each case, they start to accumulate, making maintenance more challenging as the number of states increases. This situation sets the stage for leveraging the power of parameterize to streamline and refine our testing approach. Now let's see how we can implement parameterize in our tests using Pytest. The example starts by importing the necessary modules, including Pytest and the cod class from our cods module. We utilize the @Pytest mock parameterize decorator to specify the parameters for our test function, test finish. This decorator allows the function to be executed multiple times with different sets of arguments, making it highly efficient. Specifically, we define start summary and start state as parameters. The decorator includes a list of tuples, each representing a different scenario for the test function, such as initializing a code with a summary and its corresponding state. In the test finish function, we create a cod instance with the provided parameters, then add it to the cods DB. After marking the cod as finished, we retrieve it from the database and assert that its state is done. By using this approach, we maintain a clear and concise structure that eliminates code duplication and enhances maintainability. Each test execution processes a distinct input scenario, allowing for targeted testing and easier diagnosis of issues when they arise. This method effectively showcases the power of parameterize in creating organized and efficient test cases. Now let's implement the following fixture that demonstrates how to use fixture parameterize in Pytest. Here, we define a fixture called startState that utilizes the Pytest fixture decorator alongside the params argument, which allows it to cycle through 3 predefined card states: done, in prog, and to do. Each time a test function requires this fixture, it will use one of these states. Next, we create a test function named testFinish that takes in the card's DB database and the startState fixture as its parameters. Within this function, we instantiate a new card object with a summary and the dynamic state provided by the fixture. The card is then added to the card's DB, which simulates adding it to a task management system. We invoke the finish method to transition the card to the finished state, followed by retrieving the card from the database. Finally, the test asserts that the card state is indeed done, ensuring that the state transition is functioning correctly for all variations provided by the fixture. This method not only streamlines the testing process, but also enables the reuse of setup logic across multiple tests, enhancing code maintainability. Now let's take a look at a more advanced method of parameterize in Pytest using the Pytest-GenerateTests hook. This technique allows us to create dynamic parameters for our tests based on certain conditions. In this example, we define the function Pytest-GenerateTests, which receives a metafunc argument. This argument contains metadata about the test function that is currently being processed. The first step in the Pytest-GenerateTests function checks whether the startState fixture is present in the metafunc fixture names. If it is, we dynamically parameterize the startState fixture with a list of possible states: done, in prog, and to do. This means that whenever a test function requests the startState fixture, it will run multiple times with each of these values. Next, we define the testFinish function, which takes card's DB and startState as parameters. Within this function, we instantiate a card object with a specified state and add it to the database. After marking the card as finished, the test asserts that its state is done. This approach allows our test function to adapt flexibly to different scenarios without the need for repetitive code, facilitating more comprehensive testing with minimal effort. Just imagine tailoring your tests to adapt dynamically based on user input or environmental variables. One key takeaway here is that all 3 types of parameterize, function parameterize, fixture parameterize, and hooks, offer distinct advantages. You might choose to use one over the others based on the specific needs of your tests. To summarize, parameterize is a core feature of Pytest that allows you to run a single test function with multiple sets of data, lavishly simplifying your codebase while ensuring extensive test coverage. By using both function and fixture parameterizes and leveraging powerful hooks, you can craft a versatile test framework that adapts to various scenarios. In conclusion, parameterize in Pytest is a game changer. By reducing repetitive code, providing clarity in test outputs, and broadening the scope of testing scenarios, it empowers developers to focus on building robust applications rather than wrestling with test cases. So remember, when in doubt, consider parameterize to streamline your testing process. In this lesson, we'll delve deeper into advanced parameterize techniques in Pytest. These techniques will help you navigate complex parameter set needs that can arise as you start implementing parameterize in your testing frameworks. So far, we learned about parameterize in Pytest, which facilitates running multiple test cases with a single function definition, reducing redundancy and improving code organization. We explored the use of the Pytest, mock, parameterize, decorator, allowing a single test function to handle various input states elegantly. Additionally, we discussed fixture parameterize for dynamic setups and introduced Pytest-GenerateTests, enabling more complex and flexible parameterization based on runtime decisions. Overall, Parameterize enhances test coverage and clarity while simplifying the testing process. Now we will cover advanced techniques, which will take your test automation skills up a notch. Now let's implement the following example of nested parameterize in Pytest, which showcases how to handle multiple sets of parameters efficiently. Here, we use the @Pytest, mock, parameterize, decorator twice, first to define the pairs of usernames and passwords we want to test. Each combination of username and password will allow us to evaluate different login scenarios. Next, we set up another parameterization that checks against expected outcomes, either true or false. This nested approach enables the test function, test_login, to evaluate all combinations of the provided inputs and compare the result of the login function. By asserting that the actual result matches the expected outcome, this design effectively covers various login scenarios, ensuring comprehensive test coverage. This method not only reduces code duplication, but also maintains clarity by consolidating various test cases into a single, coherent function. As the number of combinations can increase quickly, nested parameterize serves as a practical solution for managing complexity without overwhelming your test suite. Next, we will implement a fixture that showcases how to use fixture parameterize effectively in our tests. Here, we define a fixture named userRole, which is configured to accept a list of roles, specifically admin, editor, and viewer. This setup allows us to run our test function, test access control, for each user role defined in the parameters dynamically. As we proceed into the test function, we invoke the checkAccess function with the injected userRole. This function simulates the logic for determining access permissions based on the user role. In this case, if the role is admin, we assert that access should be granted. Conversely, for the editor and viewer roles, we expect access to be denied. This approach not only reduces code duplication by eliminating the need for separate tests for each user role, but also enhances our test coverage. By comprehensively checking all roles through a single test function, we maintain cleaner code that's easier to manage. Overall, this demonstrates the power of fixture parameterize to create flexible and organized test setups in Pytest. Now let's explore how we can implement dynamic test cases using the Pytest generate tests hook. This function allows us to define test parameters based on certain runtime conditions, such as the development environment in which the tests are running. Here, we check if the env fixture is present in the test function's parameters. If it is, we dynamically parameterize the tests with the appropriate environments: development, staging, and production. This approach is particularly beneficial when testing applications across multiple environments, as it ensures that the test database connection function will run for each specified environment. In this function, we establish a database connection using the environment variable past as an argument. By asserting that the result is not none, we verify that a successful connection has been established for each environment. This technique enhances testing in continuous integration, continuous deployment, CI/CD pipelines, allowing for a more flexible test suite that adapts to ever-changing configurations. Now let's implement a method to load test data from an external JSON file, which is especially useful for defining expected results in a structured manner. In our example, we create a fixture named testData that reads from a file called testdata.json. This file contains an array of objects, each with an input and an expected key representing different test conditions. Using the JSON module, we open the file and return its contents as a Python object. This data can then be utilized in our test function, test API response, using the @Pytest, mock, parameterize decorator. By passing the loaded data into the test function, we can dynamically test multiple cases. Each test case created from this data will attempt to log in with the provided input and assert that the response status matches the expected outcome. This structure not only centralizes our test data, facilitating easier updates in case of changes, but also fosters a clear separation between test logic and data management, enhancing the maintainability of our test suite significantly. Thus, if any expected outcomes change, we can simply update the JSON file, streamlining the testing process. Now let's take a look at how to combine fixtures with parameterization to enhance the testing process. In this example, we create a fixture named sample fixtures, which returns a dictionary containing some sample data. This setup allows our test to have a consistent context or configuration that it can rely upon. Next, we define a test function called test_combined, which is decorated with @Pytest, mock, parameterize. This decorator sets up two parameterized inputs, input data and expected output, which represent various test scenarios. Each combination of input will be evaluated against the expected output to ensure that the functionality works as intended. When the test function executes, it leverages the sample data provided by the fixture alongside the parameterized inputs. This synergy allows the test to process the input data in a context defined by the fixture's output. By doing so, we not only validate the logic of our function against varied inputs, but also maintain a robust testing approach that blends contextual setup with diverse scenarios effectively, ensuring comprehensive coverage and validation. Now let's implement a custom parameter validation mechanism to ensure that only valid inputs are processed in our tests. This approach starts with defining a validator function that checks if the incoming parameter meets the required criteria. In this case, the function validates whether the provided value is part of an accepted list of params, valid1, valid2, or valid3. If an invalid parameter is encountered, it raises a value error, providing a clear message about the specific issue. Next, we'll utilize the @Pytest, mock, parameterize decorator to create a test function that takes a parameter named testInput. In this scenario, we deliberately include a valid input alongside an invalid one, which allows us to demonstrate the functionality of our validator. Within the test function, we call the validator with the testInput, effectively filtering the input before asserting the expected behavior. If the input is valid, the assertion will pass. If not, an error will be raised, aiding in identifying issues quickly during test execution. This technique enhances test reliability and eases debugging, providing a solid safeguard against erroneous data in your testing framework. Next, we will implement a practical example demonstrating how to optimize parameter management in our tests. In this case, we define a constant list called validUsers, which holds tuples of valid usernames and their corresponding passwords. By employing the @Pytest, mock, parameterize decorator, we link these constants directly to our test function, testUserAuthentication, which checks user authentication against the provided username and password combinations. This approach enhances the readability of the test code, making it clear what inputs are being validated. It encourages better comprehension among developers by presenting a straightforward representation of what the test intends to verify. By centralizing user credentials in a constant, any updates or modifications to the test parameters can easily be managed, leading to improved maintenance practices. This method is particularly useful in scenarios where multiple tests require the same user data, ensuring consistency and reducing redundancy throughout the test suite. Thus, it not only streamlines the testing process, but also helps in sustaining high code quality, facilitating easier collaboration among team members. In conclusion, advanced parameterized techniques in Pytest empower you to handle complex testing environments with ease. From nested parameterize, dynamic decisions based on runtime conditions, to loading parameters from external files, each method listed above enhances your capability to maintain robust test suites. As you adopt these advanced techniques, you'll find that your tests not only grow in number, but also in depth and quality, fostering a culture of thorough testing and ultimately ensuring the reliability of your applications. Happy testing, and remember, with great power comes great responsibility, so tidy up your... In Pytest, markers are a way to tell Pytest there's something special about a particular test. You can think of them like tags or labels that enhance the way your tests are categorized, managed, and executed. If you have tests that are particularly slow, you might decide to mark them with @Pytest, mock, slow, allowing you to exclude them from test runs when you're in a hurry. Alternatively, you might group tests into subsets that serve specific purposes, mocking them with @Pytest, mock, smoke to indicate they're critical. These can be run first in a continuous integration pipeline. Essentially, mockers add a layer of modularity to your tests, allowing you to execute only those that are relevant under certain circumstances. Now let's take a look at how we can utilize built-in mockers in Pytest, specifically focusing on Pytest, mock, skip, and @Pytest, mock, xfail. The first example demonstrates the use of the @Pytest, mock, skip mocker, which is employed to skip tests that are not currently relevant. Here, the function test not yet implemented is mocked to skip execution entirely, even though it contains an assertion that would ordinarily fail. This feature is particularly useful for temporarily disabling tests during development or when certain functionalities are not yet ready. In contrast, the second example shows how to implement the @Pytest, mock, xfail mocker. This marker is applied to the test expected failure function and indicates that a failure is anticipated. If this test fails, it will be recorded as an expected failure, meaning it will not contribute to the overall test failure count. This capability is beneficial for monitoring known issues in your code without affecting the overall success of your testing suite. Overall, these markers enhance test management and allow for more effective test execution based on current development needs. Now let's see how we can implement a custom fixture in Pytest that leverages markers with parameters for enhanced test flexibility. We start by defining a fixture named items_db, which utilizes the request object to access the closest marker called numItems. This marker allows us to specify how many items the fixture should generate. If the marker is present, the fixture creates a list of item strings according to the specified number. Next, we define two test functions, test with 5 items and test with 2 items, each marked with different values for numItems. The first test ensures that the fixture populates 5 items as expected, while the second test verifies that only 2 items are created accordingly. This approach not only demonstrates the utility of custom markers, but also showcases how they can dynamically tailor fixtures to fit varying test scenarios. By implementing this code, we gain a robust mechanism to customize our test environments and validate conditions based on specific inputs, enhancing the overall effectiveness of our testing strategy. Next, we will write the following configuration to declare custom markers in a Pytest-Ini file. This is essential for informing Pytest about markers we intend to use, so it doesn't issue warnings regarding unknown markers during test execution. In our example, we define several markers. Smoke to label tests as part of the smoke testing suite, performance to categorize tests that evaluate performance, and numItems to designate a variable representing the number of items needed in certain tests. Now, let's see how we can execute specific tests based on these markers using command line instructions. For instance, if we want to run only the smoke tests that were marked correspondingly, we can utilize the command. Alternatively, should we wish to run the entire suite except for the smoke tests, we use a slightly different command to exclude them from the execution. This selective execution allows for a more efficient testing process, where developers can focus on relevant tests tailored to their immediate needs, optimizing the testing workflow without running unnecessary tests each time. Next, let's see how we can combine markers using logical operators to refine our test selections in Pytest. When we want to run specific subsets of tests, we can utilize the command line with logical expressions involving different markers. For instance, if we want to execute only those tests that are categorized as both smoke tests and performance tests, we can do so by using the command that includes both markers combined with and. This approach allows us to ensure that we are focusing our testing efforts on critical areas that meet certain criteria. Conversely, If the goal is to run performance tests while specifically excluding any that are marked as slow, we can leverage the not operator. By doing so, we maintain the efficiency of our test suite while omitting those tests that we recognize may cause delays. This flexibility afforded by logical operations on markers not only enhances our testing precision, but also ensures that we manage our testing resources effectively. Thus, by applying these techniques, we can create a targeted and efficient testing strategy that aligns with our development goals. Now let's implement the following enhanced fixture that utilizes Pytest markers to dynamically adjust the number of items in our test environment. Here, we define a fixture called items.db, which is designed to pull in parameters from a specific marker named numItems. This marker allows the user to specify how many items should be generated for the test. In our fixture, we use the request object to access the closest marker to the current test and retrieve its arguments. If the marker is present, the fixture creates a list of items based on the number specified, effectively allowing each test to operate with a customized set of items. This not only streamlines the testing process, but also minimizes repetitive coding, since different tests can simply adjust the marker value to fit their needs. Next, we will write a test function that utilizes this fixture, mocking it with @Pytest, mock, numItems3. This tells Pytest to call the fixture to generate 3 items whenever the test runs. The car assertion in the test confirms that the length of the generated items.db matches the expected number specified by the marker, ensuring our parameterization logic is functioning correctly. This approach exemplifies how to centralize and reuse code, making test management more efficient and scalable. Now let's take a look at how we can utilize Pytest markers in conjunction with fixtures to configure our test database dynamically. The code defines a fixture called dbSetup, which leverages the request object to retrieve a marker named numCards. This marker allows you to specify the number of sample cards to populate in the database before the tests are executed. When the fixture is called, it checks if the numCards marker exists. If it does, the fixture extracts the number of cards to add from the marker's arguments and populates the database accordingly. This flexibility enables different tests to operate with varied database states simply by changing the marker annotation. In this example, we've also defined a test function, test.db with 2 cards, annotated with the numCards marker set to 2. This means that before running the test, the fixture will add 2 sample cards to the database. Consequently, when the test is executed, it verifies that the card count in the database matches the expected value, demonstrating how the integration of markers and fixtures can streamline test setup and management effectively. Now let's take a look at how to inspect and list all available markers in your testing environment. You can easily gain insights into the markers you've defined, both custom and built-in, by utilizing the command Pytest markers. This command provides a comprehensive list that outlines all the markers at your disposal, which is particularly helpful as your project grows and the number of markers increases. By visually inspecting your markers, you can quickly assess their purpose and ensure they are being used correctly, which can significantly streamline your testing workflow. This clarity not only minimizes potential mistakes in your tests, but also enhances your overall understanding of the testing framework. Keeping track of your markers fosters a more organized testing process and allows you to focus your testing efforts effectively, especially when managing complex projects with many test cases. So, remembering to use this command frequently can keep your testing strategy efficient and manageable. Finally, it's important to be aware of best practices when using Pytest markers. While markers are powerful tools for managing tests, overusing them might lead to complexity and confusion. It's prudent to apply markers only when necessary and to maintain a clean structure in your test organization. To sum up, we've explored a variety of aspects revolving around Pytest markers, from built-in options to creating custom markers tailored to your testing needs. We've discovered how markers can enhance the functionality of Pytest, allowing for selective testing, flexible parameterization, and effective management of test execution. In this lesson, we've covered what markers are, how to use both built-in and custom markers in Pytest, and how they can improve your testing strategy. Leveraging these features, you can not only enhance your workflow, but also make your testing efforts more structured and manageable. Now go ahead, experiment with the power of markers in your tests, and unlock a new level of testing. Now let's take a look at how we can utilize the Pytest mock skip marker to manage test execution effectively. In this example, we see the definition of a test function named test_feature_not_ready. This function is annotated with the Pytest mock skip marker, accompanied by a reason indicating that the feature is not implemented yet. By applying this marker, we signal to Pytest that this particular test should not run during the test suite execution, which is especially useful when the code being tested is either incomplete or temporarily disabled. When the test suite is executed, Pytest recognizes the skip marker and produces output that informs us that the test was intentionally skipped, rather than reflecting it as an error or failure. This approach helps maintain clarity in our test results, allowing developers to concentrate on relevant tests without being distracted by unrelated failures. Essentially, using Pytest mock skip promotes a cleaner and more organized testing process while enabling teams to focus on code areas currently under development. Next, we will write a test that is intentionally expected to fail by utilizing the Pytest mock xfail marker. This marker is particularly useful for scenarios where you know a test will not pass due to an existing issue in the code or if you are still developing a new feature. In our example, we annotate the test function with known issue with this marker, providing a reason for its expected failure. The reason states that there is a known issue with this function, as it currently does not return the expected output. When executing our test suite, Pytest will recognize this annotation and allow the test to fail without negatively impacting the total success count. This means that, while the test fails, Pytest will report it as an expected result. This feature is invaluable for tracking ongoing work, as it keeps our test results clean and focused on tests that are actually passing. Thus, we can manage our code development effectively without clutter from known issues, signifying a well-structured testing approach as we drive forward with our coding task. Now let's take a look at how we can conditionally skip a test in Pytest using the Pytest mock skipIf marker. This marker allows us to specify a condition under which the test will be skipped, ensuring that only relevant tests are executed based on the environment they are running in. In this example, we check if the system platform is Linux by utilizing sys platform. If the platform is anything other than Linux, the test will not run, and instead, it will be skipped with a specific reason provided. This test only runs on Linux. Through this conditional skipping, we tailor our testing suite to accurately reflect the environments in which our code is intended to operate. The test function defined here, test Linux-specific functionality, will assert true only when the test is executed on a Linux system. This mechanism not only optimizes the testing process, but also enhances clarity, as tests that aren't relevant for the current environment won't contribute to potential confusion or erroneous failure reports. This refined approach strengthens our overall testing strategy, particularly in diverse development environments where certain functionality may not be applicable. Now let's take a look at how we can combine markers to create sophisticated test selection logic in Pytest. In the code snippet, we've defined a test function named test_smoke_with_expected_failure. This function is decorated with two markers, @Pytest mock smoke, which signifies that it is part of the smoke tests, and @Pytest mock xfail, indicating that we expect this test to fail. By mocking the test as part of the smoke tests, we signify its priority in our testing suite, focusing on essential functionalities. The xfail marker is particularly useful here, allowing us to document known issues without affecting the overall test results, essentially telling Pytest to treat this failure as expected. When we run our tests with the command to execute smoke tests, This specific test will still run, but its expected failure won't count against the success metrics, helping keep our test output clean and informative. This way, we maintain clarity in our testing strategy, ensuring critical functionalities are tested while also managing ongoing issues effectively. This combination of markers empowers us to conduct focused testing, improving our overall testing workflow. Next, we will introduce how to use markers specifically for heavy integration tests. In this example, we will mark a test function as an integration test using @Pytest-Mock integration. This allows us to categorize this particular test, which might require extensive setup and execution time, as part of a broader suite of integration tests. Such organization not only enhances clarity in your testing framework, but also allows you to control when these tests are run, ensuring they don't unnecessarily impact your development speed during quick feedback cycles. Now, let's see how we can call our test suite to run specific tests using the command line. By employing the Pytest command with the M flag followed by a filter like smoke or integration, we can selectively execute tests tagged with either of those markers. This flexibility is especially crucial in continuous integration, CI, environments, where you might want to quickly verify critical functionalities with smoke tests while scheduling heavier integration tests to run less frequently. This strategic approach ensures a balanced test execution process, optimizing our development lifecycle and maintaining focus on what truly matters as our code evolves. Now let's see how we can implement custom markers in our Pytest test suite. By documenting your markers in a Pytest-Ini file, we ensure that all team members are aware of the purpose and categorization of various tests. This practice not only enhances clarity when the number of tests increases, but also facilitates easier maintenance of the test suite as it evolves. In the example provided, we declare two custom markers, smoke and integration. The smoke marker identifies tests that are part of a minimal set of tests run to ensure the most critical functionalities are working after changes, while the integration marker categorizes tests that assess interactions between different components of the system. Having this clear structure helps your team quickly recognize the focus of each test. Furthermore, this declaration allows Pytest to recognize these markers during test runs and enables static analysis tools to validate their use across your codebase. This way, teams can maintain organized and efficient testing workflows while minimizing confusion related to test execution conditions. Now, let's take a look at how to query the available markers in Pytest using a simple command. By executing Pytest markers, in your terminal, you can gain a clear overview of all the markers that have been defined in your test suite. This command is particularly useful for avoiding mistakes and miscommunications regarding which markers are currently in use. Understanding the available markers enables you to adapt your testing processes quickly in response to evolving requirements. It fosters an organized approach to managing your tests, allowing you to ensure that your suite aligns with your development goals. This practice of reviewing markers not only enhances clarity, but also helps maintain a well-structured testing framework. By integrating this command into your routine, you empower yourself to write cleaner and more maintainable tests, ultimately leading to a more efficient testing workflow. This systematic approach enhances your overall Pytest experience, ensuring that you can navigate your test suite effectively and adapt. Let's dive into the essential aspects of developing a test strategy for your project. A robust test strategy is vital in ensuring that the software performs as intended while minimizing bugs. In this session, we're going to explore how to write a test strategy and what key components to include to create an effective testing framework. So far, we learned about Pytest's built-in markers for test management, and now we will cover the goals, prioritization, and implementation of a comprehensive test strategy. A test strategy outlines how testing will be conducted throughout the software development lifecycle. It sets the direction for what to test, the method of testing, and the resources required. The questions we need to answer include which features require testing, what levels of tests are necessary, and how can we organize these tests effectively. Let's start by determining the scope of our test strategy. Not all projects are created equal. Some necessitate extensive testing due to the nature of their functionality. Think air traffic control systems. Others, like simple command line applications, might not need that same level of scrutiny. For our purposes, we'll focus on user-visible functionality and prioritize what needs testing based on several key considerations. Recent changes. Any new features or modifications should be a priority to verify everything is still functioning correctly. Core functionality. Identify essential functions that must work reliably for users to effectively utilize the software. Risk assessment. Understand which parts of the application are prone to bugs or significant errors. This could be features that industry standards dictate must be reliable. Problematic areas. Areas that have shown frequent defects in the past should be tested thoroughly. Asterisk expertise. Features requiring specialized knowledge should be examined closely due to potential gaps in understanding. Now let's implement a function that facilitates adding a card to our task management application. The addCard function takes 3 parameters: the database DB, a summary for the card, and an optional owner. Initially, it checks if the summary is provided. If not, it raises a value error, ensuring that a card cannot be created without this critical detail. This validation step is crucial for maintaining data integrity. Next, the function calculates a unique carded based on the current length of the database, ensuring each card has a distinct identifier. It then constructs a card dictionary, encapsulating the ID, summary, and owner, and finally appends this dictionary to the DB. The function returns the newly created card, making it readily accessible for further processing. To test this functionality, we'll create a series of tests within the test_addCard function. By asserting that the function correctly handles valid inputs, raises an error for missing summaries, and checks if duplicate cards can be added, we ensure that our implementation meets the desired specifications. This testing process underpins our commitment to developing a robust application. The next aspect of our test strategy lies in documenting our initial findings. By recording all features to be tested, along with their expected behaviors and initial test cases, we create a concrete reference point. For instance, we might document like below. Feature asterisk, add a card. Test cases asterisk. Happy path, adding a card with a valid summary. Error state, adding a card with an empty summary. Boundary case, adding duplicate cards. By structuring our test cases in this manner, we provide a clear outline that can be referenced during future testing sessions or for new team members. Once we have established our test cases, the next logical step is to prioritize these tests. Here's where we will develop criteria for our testing strategy, focusing more on the non-trivial, happy path scenarios first. Why? Because these cases generally involve the most frequent use of the application and ensure that its key functionalities work as intended. A great way to structure the prioritization is to categorize tests into tiers. Tier 1 ***, critical functionalities that should always work, such as adding or deleting a card. Tier 2 ***, important features with lower user impact, like updating card information. Tier 3 ***, nice-to-have features, such as metrics or performance analysis, that can be tested later after core features are solidified. This tiered approach ensures our team focuses efforts where they matter most. Now let's take a look at how we can structure our test files for better organization and maintainability. In our example, we create a directory named tests that will house different test files corresponding to various functionalities of the application, such as adding, deleting, updating, and listing cards. This clear separation allows developers to easily locate tests relevant to specific features, which is especially handy as the project grows. Next, we will write the test cases for adding a card using the Pytest framework. In the test_add.py file, we start by importing the necessary components, including the Pytest, library, and the function addCod from our application code. We then define our test for adding a cod, beginning with a test case that verifies the functionality when correct details are provided. The test checks whether the cod's summary and owner attributes match the expected values after the cod is added successfully. Additionally, we implement a test case to ensure that the function raises an error when an attempt is made to add a cod without a summary. This approach guarantees that our application behaves as expected under different scenarios, which is critical for a robust testing strategy. Finally, we should understand the importance of continuous improvement of our test strategy. Regularly scheduled reviews of our testing outcomes compared to expectations will help us refine our test cases, modify our priorities, and adapt to changes within the software. Additionally, utilizing analytics to predict potential risks can enhance our preparedness for future development cycles. Adequately documenting and sharing these insights can lead to continuous dialogue within the team, ensuring that everyone remains aligned with the testing goals and strategies. It's not just about having a plan, it's about evolving the strategy as the project progresses. In summary, a sound test strategy is the backbone of a reliable software application. By clearly defining goals, evaluating risks, and systematically implementing tests, we can guarantee that our software meets the expected standards. So far, we covered the foundational aspects of writing a test strategy. Going forward, remember the importance of documentation, prioritization, and adaptability in the test processes for successful software. Now let's take a look at how we can implement a function that adds a cod to our database. The addCod function accepts two parameters, db, which represents our database as a list, and summary, the description of the cod being added. It first checks if the summary is empty, and if so, raises a value error to ensure that every cod has a summary. If the summary is valid, the function generates a unique coded by taking the length of the current database and adding one, thus ensuring that each cod has a unique identifier. It then creates a dictionary representing the cod with its ID and summary, appends this dictionary to the DB, and returns the newly created cod. Next, we will write a test function, test_addCod, to confirm that our addCod function behaves as intended. In this function, we initialize an empty list to serve as our database and proceed to test a happy path scenario by adding a cod with a valid summary. Buy groceries. We use an assertion to verify that the returned cod matches our expectations, confirming that the function properly creates and returns the cod while updating the database correctly. This systematic approach reinforces our testing strategy and aims to ensure that the function performs accurately under specified conditions. Next, we will write the following test function to handle potential error cases when adding cods. The function, test_addCod error cases, is designed to ensure that our addCod function behaves correctly under various adverse conditions. Initially, we create an empty database represented by a list. The first test checks whether attempting to add a cod with an empty summary raises a value error. In this specific scenario, if addCod is called with an empty string, the function should raise the error message, summary is required. We handle this by using a try_except block to catch the exception and then assert that the message matches our expectation. Next, we test the functionality of adding a duplicate cod. After initially adding a cod with the summary, walk the dog, to the database, we attempt to add the same cod again. The expected outcome is that the addCod function should return a new cod object with an incremented ID, thereby confirming that our implementation correctly handles duplicate entries. This thorough approach in our test cases helps validate the robustness of our application, ensuring it can manage both expected and erroneous inputs gracefully. Next, we will implement a function called deleteCod, which is responsible for removing a cod from a database represented by a list. The function takes two parameters, db, which is the list of cods, and coded, the identifier of the cod to be deleted. Before proceeding with the deletion, the function checks if the coded provided is valid by ensuring it's within the valid range. If the coded is less than or equal to 0 or exceeds the length of the DB, a value error is raised with an appropriate message. Now let's take a look at how we can develop the corresponding test function, test_delete_cod. This function initializes a sample database with 2 cods and tests 2 key scenarios. First, it verifies the successful removal of the first cod, asserting that the cod returned matches the expected output and checking that the database length is updated accordingly. Next, we consider an edge case where an invalid coded is used for deletion. Here, we expect a value error to be raised, and the test ensures that the error message is correct. Together, these tests ensure robust functionality for our delete operation and highlight the importance of handling both expected and unexpected input. Next, we will implement the function to count the number of cods in the database. The countCods function takes a database represented as a list and returns its length, effectively giving us the total number of cods stored. This simplicity ensures that we can easily verify the cod count at any point in time. Now let's see how we can create test cases for this function with the test_countCods function. First, we initialize an empty database and assert that the count of cods is 0, ensuring our function behaves correctly when there are no cods. Following that, we simulate adding a cod using the addCod function, let's say, a cod titled Go Shopping. We then check that the count reflects this addition, confirming that our system updates the cod count accurately. Finally, we add another cod, Read a Book, and again assert the count, verifying that our counting mechanism is robust even as more entries are added. Overall, these tests not only validate the expected behavior of the countCods function, but also reinforce our application's ability to reflect user interactions seamlessly. Now let's take a look at how we can structure our test cases in a way that promotes clarity and organization. We will create a dedicated directory layout for our tests within the project, separating them by functionality. For instance, when testing features related to cod management, we can set up individual files such as test_add_py, test_delete_py, and test_count_py. Each file will correspond to specific features of the application and will contain relevant test cases to ensure functionality. In test_add_py, we will define tests focused on the functionality of adding cods, encapsulating different test scenarios, including both happy paths and error cases. This helps keep our tests organized and makes it easier to navigate through them when additional developers are involved in the project. As we implement these tests, we will utilize Pytest to execute our test cases. The use of Pytest allows for a streamlined approach, enabling quick identification of passed or failed tests. This organization not only aids in understanding the current state of testing for each feature, but also enhances collaboration among team members, ensuring everyone is aligned on the testing goals for each feature. Collaboration is paramount in the testing process, especially when working across teams. Regularly discussing test cases and their expected behaviors with your team or domain experts helps ensure that nothing is overlooked. As new features are added or existing ones modified, returning to your test list and updating it accordingly is essential. This iterative process allows for continuous improvement and alignment within the team. Always expect that your initial list of test cases will grow over time. This might include new scenarios, unforeseen edge cases, or tweaks in functionality as features evolve. The idea is to remain agile and receptive to feedback within your team, which contributes to a more robust test suite that better captures the software's functionality. All in all, crafting effective test cases is a comprehensive process that lays the groundwork for a successful testing suite. By applying a methodical approach to developing cases, thoroughly considering edge and error scenarios, and consistently collaborating with your team, you can create a robust framework that enhances your software's reliability. Embracing this testing culture can help you sleep soundly at night, knowing that your application is well tested and ready to serve its users. In this video, we'll explore Pytest configuration files, which play a crucial role in optimizing how Pytest operates during testing. By the end, you'll understand how to leverage these files to save time and reduce redundancy in your testing process. So far, we learned the significance of creating effective test cases in software development, emphasizing their role in identifying bugs and providing documentation. We explored the process of developing test cases, focusing on happy path scenarios as well as edge and error cases to ensure comprehensive coverage. The lesson highlighted the importance of organizing tests methodically, using tools like Pytest, and fostering collaboration among team members to continuously improve the testing suite. Now, we will dive deeper into how we can use Pytest configuration files to enhance our testing workflow. Now let's take a look at a simple Pytest configuration file, which can streamline our testing process by defining key parameters. The Pytest section indicates the beginning of the configuration, where we specify settings that influence how Pytest discovers and runs our tests. Next, we define the test paths option, which directs Pytest to search for test files within the specified tests directory. This organization helps maintain a clear structure, ensuring that all tests are located in one place. Following that, the Python files entry specifies which files Pytest should consider as test files. By using the wildcard pattern test**py, we instruct Pytest to include any Python files starting with test, making it easy to identify our test cases conventionally. Finally, the log cli level setting allows us to control the verbosity of logs in the command line interface. By setting it to info, we ensure that we receive informative log messages during our test runs, enhancing our ability to monitor the testing process and identify issues efficiently. This setup ultimately contributes to a more effective testing experience. Now let's explore how we can enhance our Pytest configuration using the addops option in the Pytest-Ini file. By adding the line addops equals v_maxfill, we can customize the way Pytest runs our tests. The v flag activates verbose mode, which gives us detailed output for each test that runs. This feature is incredibly useful because it provides immediate feedback, allowing us to see which tests are passing or failing and understand their behavior better. Additionally, the maxfill equals 5 option sets a limit on the number of test failures before Pytest stops executing. This is particularly advantageous in large test suites, as it prevents the console from being flooded with information after a certain point. By stopping after 5 failures, we can focus on addressing critical issues first without sifting through excessive outputs. Overall, this configuration dramatically streamlines our testing workflow, making it more efficient and manageable by fostering a quicker feedback loop on our code's stability. Now let's see how we can implement custom markers in our Pytest-Ini file. Markers are an essential feature that allows us to categorize tests based on their specific attributes or execution characteristics. In this example, we define 2 custom markers: slow, which marks tests that might take a significant amount of time to run, and smoke, which labels tests that are part of the basic functionality check of the application. Once these markers are defined, we can easily apply them to particular test functions. For instance, we have a test called testlongProcess, which simulates a lengthy operation and is designated with the @Pytest mock slow decorator. This helps us identify it as a test that may require extra time during execution. Similarly, we have test basic functionality, marked as part of the smoke tests, confirming that the fundamental logic of the application works as expected. This categorization enhances our ability to run specific groups of tests. For example, by using command line options, we can execute only the slow tests by appending the mslow flag when we run Pytest, thereby streamlining our testing process and focusing on essential tests as needed. Now let's take a look at how we can implement a fixture for managing database connections in our tests. The @Pytest Fixture decorator allows us to define a setup function that will execute before any tests that require it run. In this case, we are specifying that our fixture, named setupDatabase, has a session scope, meaning it will be invoked once per test session and shared among all tests that utilize it. Inside the fixture, we can place our setup code, such as initializing a database connection. The yield statement is crucial here. It allows the test to run with the established connection, and once the tests are completed, the code following the yield statement will execute to clean up the connection, ensuring no resources remain allocated unnecessarily. Next, we will write a test function, test_data_integrity, which takes setup_database as a parameter. This means that when this test runs, setup_database will automatically provide the database connection. Inside the test, we can perform queries and assertions, such as checking that the results from the user table are not none, thereby validating the integrity of the data. This approach not only keeps our tests organized, but also guarantees consistency across tests when accessing the database, efficiently managing our testing environment. Now let's take a look at the Nockasedias option in our Pytest-Cov configuration file. This feature allows you to instruct Pytest to ignore specific directories during test discovery, which is particularly useful when you have legacy tests or directories that you want to keep for reference but don't want to clutter your test output. By adding Nockasedias equals old tests, we tell Pytest to skip the old tests directory whenever it is scanning for test files. This keeps your current testing sessions focused and free from distractions, as Pytest will not run tests located in that directory. Maintaining a clean testing environment is crucial, especially when working on active development projects, as it allows you to prioritize relevant tests and avoid unnecessary noise in your results. Therefore, this configuration option not only enhances your workflow, but also helps you manage your testing framework more effectively, ensuring that only pertinent tests are executed during your testing cycle. Now let's implement the following configuration in our Pytest-Cov file to enable coverage reporting. The line addops equals cov equals miproject coverpot equals HTML instructs Pytest to include coverage metrics for our specified project directory, in this case, miproject. This configuration uses the Cov option to activate the coverage plugin, which allows Pytest to collect data on how much of our code is being tested. By providing the folder name, we tell Pytest where to look for the code that's being executed during the tests. Additionally, the coverpot equals HTML option directs Pytest to generate a coverage report and save it as an HTML file after the tests have run. This report is invaluable as it visually presents insights into the testing coverage, allowing you to identify both the well-tested areas of the codebase and those that need more attention. The automatic generation of this report every time Pytest runs streamlines the process of maintaining code coverage oversight, improving your testing workflow, and ensuring comprehensive verification of your project's functionality. Now let's take a look at the configuration settings defined in our Pytest-Cov file. The first line, test paths equals tests, specifies that Pytest should search for test cases within the tests directory. This helps streamline your testing process by directing Pytest to the location where all your test files are organized, reducing the likelihood of unnecessary clutter from unrelated files. Next, we have log cli level equals info, which sets the logging level for the command line interface. By configuring logging to the info level, you ensure that detailed logs will be provided during test execution, allowing you to monitor the progress and behavior of your tests effectively. This level of feedback is particularly useful during development, providing valuable insights as you work through test cases. Implementing these configurations not only enhances the clarity and efficiency of your testing workflow, but also ensures all team members have a uniform experience, ultimately fostering better collaboration and consistency throughout your project. As we wrap up this lesson, let's quickly recap what we've covered. We started with an introduction to Pytest configuration files, understanding their purpose and significance in saving time and effort. We explored creating a basic Pytest-Cov file, setting up logging levels, and managing project paths, then jumped into more advanced configurations like adding command line options, creating custom markers, and defining global fixtures. Now, as we move forward in our testing journey, remember to utilize these configuration features in Pytest to enhance your tests' efficiency and maintainability. This knowledge will empower you not only to write more effective tests, but also to cultivate a collaborative and organized testing framework among your team. Thank you for joining me today, and continue to embrace the power of configuration. Both Coverage.Py and Pytest-Cov are essential tools for measuring test coverage in Python projects. In today's lesson, we'll explore how to set them up and use them effectively to ensure your tests are covering the code they should. So far, we learned the importance of Pytest configuration files in optimizing the testing workflow, allowing for consistent parameterization and the elimination of redundancy. We discussed creating a basic Pytest-Ini file to manage paths, logging levels, and additional command line options. The lesson also covered advanced configurations such as custom markers, global fixtures, and the integration of plugins to enhance testing capabilities. Now we will talk about using Coverage.Py with Pytest-Cov to enhance your testing framework. Now let's write the following command to install the necessary packages for measuring test coverage in our Python project. The command pip install coverage Pytest-Cov utilizes pip, Python's package manager, to install two essential tools, Coverage.Py and Pytest-Cov. Coverage.Py is a standalone tool that helps in measuring how much of your code is executed during testing, while Pytest-Cov integrates this coverage measurement with Pytest, allowing you to assess your tests as they are executed. By running this command in your terminal or command prompt, you ensure that both packages are readily available for use in your project. Once the installation is complete, you will be equipped to begin leveraging these tools to generate coverage reports. This will enable you to evaluate which parts of your code are being tested effectively and which may require additional test cases, giving you insights to improve your code quality and testing practices. Next, we will explore how to run tests with coverage measurement using the Pytest framework along with Pytest-Cov. To begin measuring coverage for a specific module, you can use the command Pytest-Cov equals my module. This command instructs Pytest to execute all test cases associated with my module, Py, while simultaneously gathering information about code coverage. It will show you which parts of your code were executed during the tests, helping you understand how thoroughly your tests are covering the functionality in that module. Now, let's see how we can measure coverage for an entire package along with test execution. You can achieve this by executing the command Pytest-Cov equals your package tests. This command is particularly useful when your tests are contained within a separate directory named tests. It measures the coverage across all files in your package as the tests from the specified directory run. This integrated approach ensures you gain insights into the overall effectiveness of your test suite, as it evaluates how well your tests cover the intended code paths in your package. Now let's take a look at the coverage report generated by Pytest-Cov after running our tests. The output summarizes the code coverage results for the specified modules, providing a quick overview of how many lines of code were executed versus how many were missed. In the report, the first column lists the names of the files being measured, such as your package init and your package my module. The SDMTS column indicates the total number of executable statements in each file. For instance, my module, Py, contains 10 statements in total. The miss column shows how many of those lines were not executed during the tests, revealing that 2 lines in my module, Py, were missed. The cover column calculates the coverage percentage, informing us that my module, Py, has 80% coverage. This percentage is crucial as it helps identify how much of the code is being tested and where there may be gaps in your testing strategy. Understanding these metrics is essential for improving test coverage and ensuring that critical code paths are adequately tested. Now let's see how we can generate a more detailed coverage report using Pytest-Cov. To accomplish this, we will use the Cov report option combined with the Cov flag, which allows us to specify the format of our report. In this case, we're opting to create an HTML report, which provides a visually appealing and user-friendly way to analyze our coverage results. Next, we will write the following command in our terminal. Pytest-Cov equals my module Cov report equals HTML. Executing this command will run all the defined tests in our project while measuring coverage for the specified module, myModule. Upon completion, it will create a directory called HTML-Cov in our project folder. Within this directory, an index, HTML file will be generated, which we can then open in a web browser. This index file presents our coverage data in a color-coded format, making it easy to identify covered and uncovered lines of code at a glance. This enhanced reporting approach not only improves our understanding of coverage, but also aids in pinpointing areas that may necessitate additional testing efforts. Now let's take a look at how to configure Coverage.Py to ignore specific files and directories during the coverage measurement process. To do this, we create a configuration file named Coverage in the root of our project. This file allows us to specify certain paths that we want Coverage.Py to omit from its analysis. In our example, we will set up the configuration to ignore everything within the tests directory and any files located in the venv directory. By adding these paths under the omit setting in the coverage section, we ensure that the coverage report will focus solely on the relevant application code, providing a clearer view of how much of it is being tested. This approach is particularly useful when dealing with third-party libraries or areas of your project that are intentionally left untested. By having these exclusions in place, you can maintain an accurate representation of your code's coverage, making it easier to identify parts of the application that require further testing. With this configuration, you can optimize your testing strategy and focus your efforts on enhancing the quality of your core codebase. Now let's see how we can implement branch coverage in our tests to gain deeper insights into the code execution. By modifying our Pytest command to include both the cov_branch option and the cov_report equals term missing option, we enhance our coverage measurement. This command not only measures line coverage, indicating which lines of code were executed during testing, but it also assesses branch coverage, providing information about whether all possible control structures, such as conditionals, have been exercised. When you run this updated command, a report will be generated directly in your terminal, highlighting any lines and branches that were not executed during your tests. This detailed feedback is crucial, as it allows you to see not just which lines of code have been tested, but also which logical paths within your code might need additional testing. By identifying untested conditionals and missed branches, you can strategically target areas for improvement in your testing efforts, ultimately leading to a more robust testing suite and higher quality code. Next, we will write the following configuration to incorporate coverage reporting into our CI/CD pipeline using GitHub Actions. This YAML configuration sets the workflow to trigger on every push or pull request, ensuring that we consistently receive coverage reports with each code update. In this setup, the job named build runs on the latest version of Ubuntu, which ensures compatibility with various dependencies. The first step involves checking out the code from your repository, enabling the workflow to access the current version of the application. Following that, we set up the Python environment by specifying the desired Python version, in this case, 3.8. After the environment is prepared, we install the necessary dependencies, specifically Pytest and Pytest-Cov, which are crucial for running our tests and measuring coverage. The final step executes the tests using the Pytest command, with options to collect coverage data specifically for the myModule. The coverage report is saved in XML format, allowing for integration with tools like CodeCov or Coveralls, which can provide insights into coverage metrics over time. This automated process greatly enhances our development workflow by ensuring code quality is continuously assessed. To wrap up our discussion, we've explored Coverage.Py and Pytest-Cov as powerful tools to measure the effectiveness of your tests. With the ability to easily install these packages, run tests with coverage, generate detailed reports, and customize your coverage measurement, you can significantly enhance the quality of your software projects. Configuring coverage to ignore certain files and enabling branch coverage further allows for more precise insights, helping you to write better tests and improve code quality over time. By incorporating coverage checks into your CI/CD pipeline, you can maintain a high standard in your code quality as your project evolves. Always remember that the goal is not necessarily to hit 100% coverage, but to ensure that critical paths in your code are well tested, providing confidence in its reliability. In conclusion, Coverage.Py and Pytest-Cov are indispensable tools for any Python developer looking to ensure their code is thoroughly tested. Making these reports a part of your development process can foster a culture of quality, leading to better, more reliable software. Thank you for joining this session, and continue coding with well-covered tools that measure code coverage. Watch your code while a test suite is being run and keep track of which lines are hit and which are not. This process is essential for developers as it informs them about the effectiveness of their test suites and guides them in identifying parts of the code that may need more testing. Code coverage tools provide insights not only on which lines are executed, but also help detect which paths through conditional statements have been followed, offering a measurement known as branch coverage. So far, we learned about the essential tools Coverage.Py and Pytest-Cov for measuring test coverage in Python projects. We covered the installation process, how to run tests with coverage measurement, and generating detailed reports. Additionally, we discussed configurations for ignoring certain files and measuring branch coverage, which provides deeper insights into test effectiveness. Incorporating coverage checks into your CI/CD pipeline can significantly enhance code quality over time. Now we will cover code coverage tools in more detail, examining how they work, the different types of coverage they provide, and practical examples to demonstrate their importance in ensuring robust Python applications. Now let's implement a simple function that checks whether a number is positive or not. The function named checkNumber takes a single parameter, num, and uses an if-else conditional statement to determine whether the number is greater than 0. If the condition evaluates to true, the function returns the string positive. However, if num is less than or equal to 0, it returns negative or 0. This straightforward logic demonstrates how we can handle decision-making in Python using conditional statements. Next, we will write test cases for our function to ensure it behaves as expected across different scenarios. The test_checkNumber function includes assertions to validate the outputs of checkNumber for various input values. Specifically, it checks that the function correctly identifies positive numbers, as well as handles the edge cases of 0 and negative numbers by ensuring all branches of the conditional logic are tested. By covering all possible outcomes in our tests, we enhance the reliability of our application and reinforce the importance of comprehensive branch coverage in our testing strategy. Now let's explore how to utilize the Coverage.Py tool to measure test coverage in our Python projects. First, we need to install the coverage package. This is done using the command pip install coverage, which sets up the environment to start tracking code execution during testing. Next, we will run our tests while simultaneously measuring code coverage. This can be accomplished with the command coverage run mpytest, which executes our test suite and records the execution of the code lines. This combination allows us to gather useful data that highlights which parts of our codebase are tested and which remain untouched. Finally, we will generate a comprehensive coverage report. To create a visual representation of our coverage data, we can use the command Coverage.html. This action creates an HTML.cov directory filled with an HTML report that visually presents our coverage results. You can open this report in a web browser to interactively explore which lines are covered and identify areas that require additional tests, ultimately helping us improve the quality of our code and ensure robust applications. Next, we will explore the core functionality of our application by examining the code in app.py. Here, we define 3 primary functions: add, subtract, and multiply. The add function takes 2 arguments and returns their sum, while the subtract function also accepts 2 parameters but returns the difference between them. Now let's take a look at the multiply function, which introduces some essential error handling for a common edge case. It checks if the second parameter, b, is 0. If it is, the function returns a specific message, cannot multiply by 0, rather than attempting an invalid multiplication operation. This approach is crucial as it prevents runtime errors and ensures that the function behaves reliably under various circumstances. Moving on to our tests in Test-App.Py, we begin with tests for the add and subtract functions, confirming that they produce the expected results. Next, we will implement tests for the multiply function to ensure thorough coverage. This includes validating both regular multiplication and the error handling for multiplying by 0, thus enhancing the overall robustness and reliability of the code. Now let's see how we can implement a GitHub Actions workflow for our Python application. This configuration file starts with the name of our workflow and specifies it should trigger on both push and pull request events, ensuring that our testing pipeline runs whenever changes are made. The job named build runs on the latest Ubuntu environment, providing a clean slate for our tasks. Next, we'll check out the source code repository, setting up Python with the specific version we want to use. Installing the necessary dependencies is crucial, and here we're using pip to install Pytest and Coverage, which are essential for running our tests while collecting coverage metrics. Now, let's implement the actual testing step, where we run our tests using Pytest while simultaneously measuring coverage. After our tests execute, we generate a coverage report that outlines which lines of code were executed, followed by creating an HTML report for a more visual analysis of our code coverage. Lastly, we add a verification step to enforce a coverage threshold of 80%. If the coverage falls below this number, the build will fail, helping maintain high code quality throughout the development lifecycle. Let's also discuss practical tips to improve your code coverage reporting. Avoid the temptation to chase 100% coverage at all costs. While it's tempting, not every line of code requires tests. Instead, focus on covering critical paths, user interactions, and error handling scenarios. This ensures your tests are meaningful. When you run your tests and identify missed coverage, it's essential to evaluate whether those lines contain critical business logic that requires testing or if they can be safely ignored. For example, utility functions that don't contain business logic might be less critical to have exhaustive tests compared to higher-level functions that directly impact user-facing features. To summarize a key learning, it is important to strategically ensemble your testing and coverage tools to boost the quality of your software while judiciously applying tests where they provide the most value. Well-planned tests lead not only to higher coverage percentages, but also to a more reliable and maintainable codebase. As we wrap up this comprehensive exploration of coverage tools in Python, remember that they are valuable allies in your testing strategy. By effectively using tools like Coverage.Py and Pytest-Cov and integrating them into your development process, you can ensure a more robust application and reduce the risk of bugs slipping through into production. So far, we discussed the importance of code coverage, various metrics like line and branch coverage, how to utilize coverage tools, generated reports, and best practices for implementing tests successfully. In future lessons, we'll explore continuous integration methodologies in more detail and how to leverage these practices in conjunction to create a flawless workflow in your project. Now go ahead, test your code, and make sure your coverage reflects the quality of your application. Generating HTML reports with Coverage.Py is an essential skill for any Python developer looking to enhance their testing process. With these reports, you get a visually appealing and straightforward way to see how much of your code is tested and where certain gaps exist. In this session, we'll explore how to generate these reports, interpret the results, and leverage this information for improving your code quality. So far, we learned about the concept of code coverage as a measure of how much of the source code is executed during testing, focusing on metrics like line and branch coverage. We discussed essential tools such as Coverage.Py and Pytest-Cov, along with their installation and usage for tracking test coverage in Python projects. The importance of generating and analyzing coverage reports to identify gaps in testing and enhance code quality was emphasized. Moving forward, we will delve deeper into continuous integration practices and how they can be integrated with coverage tools to streamline the development workflow. Now let's see how we can implement a simple calculator in Python that we'll be testing for coverage. First, we define two functions, add and subtract. The add function takes two parameters, a and b, and returns their sum. Similarly, the subtract function also takes two parameters and returns the result of subtracting b from a. This modular approach allows for easy extension and testing of our calculator functions. Next, we need to create tests for our calculator to ensure its functionality. We will use the Pytest framework, which is a popular choice for testing in Python. In our test file, test-calculator.py, we import the functions from calculator.py and define individual test functions for each calculator operation. Specifically, test-add checks that adding 1 and 2 yields 3, while test-subtract verifies that subtracting 2 from 5 results in 3. This setup enables us to systematically assess the correctness of our calculator functions through tests. Now let's see how we can generate the HTML report using Coverage.Py. To create this report, you need to execute a simple command in your terminal, Coverage.HTML. This command instructs the coverage tool to generate an HTML report based on the coverage data previously collected while running your tests. Once executed, Coverage.Py will produce an HTML-Cov directory within your project folder. Inside this directory, you will find the index.html file, which serves as the main entry point to your coverage report. Opening this index.html file in a web browser will present you with a visually appealing and informative overview of your test coverage. The report includes overall coverage percentages and details for each file in your project. You'll be able to easily navigate through sections that highlight executed lines in green and untested lines in red. This visual representation not only helps you to quickly identify which sections of your code are lacking tests, but also provides the necessary context to improve your test coverage effectively. Now let's take a look at how to implement a new feature in our calculator, the multiply function. This function takes two arguments, a and b, and returns their product. This straightforward operation enables users to perform multiplication alongside other arithmetic functions we previously created. Next, we need to ensure that this new function is adequately tested. To do this, we'll write a corresponding test function named testMultiply. This test function will leverage an assertion to verify that when we call multiply with the arguments 2 and 3, it correctly returns 6. This is critical for confirming that our multiplication logic works as intended. By adding this test, we enhance our test coverage, ensuring that the multiply functionality is not only implemented, but also verified against expected outcomes. After we incorporate these changes, we can rerun our coverage checks and regenerate our HTML report to see the updated coverage metrics. This process will help us visually confirm that our newly tested feature is indeed covered, thereby improving the overall quality of our code. Now let's see how we can generate an HTML report specifically for a single file using Coverage.Py. First, execute your tests while measuring coverage for just the calculator.py file by running a command that specifies this file. This ensures that only the coverage data pertinent to calculator.py is collected, leaving out any unrelated files, such as your test file. Next, we will generate the HTML report focusing only on this specific file by issuing the second command. The options you provide here allow you to omit the test calculator.py file from the report results. By using the omit flag, you customize the coverage report so that it highlights the coverage statistics solely for calculator.py. This approach gives you a streamlined view of your test coverage, making it easier to identify any gaps in your tests for that particular file. This targeted analysis is especially beneficial for isolating issues or improvements that need attention in specific components of your codebase. Now let's take a look at how we can configure our coverage reports using a Coverage.Py file. This configuration file is crucial as it allows you to customize which parts of your code are included in the coverage reports. In our example, we start by specifying the Run section where we set the omit directive. This directive instructs Coverage.Py to ignore any files located in a directory named tests when calculating the coverage statistics. This is particularly useful for focusing the report on the main application code rather than the tests themselves. The next section, Report, contains the exclude lines directive, which allows us to designate certain lines that should be excluded from the coverage report. Here, we choose to exclude lines marked with pragma, no cover, effectively telling Coverage.Py to skip over any lines that are explicitly indicated as not to be counted towards coverage. This setup ensures that the report emphasizes the most relevant code, providing clearer insights into areas that need more testing attention. Incorporating these configurations will ultimately help streamline your coverage reporting, making it easier to identify critical gaps in testing. Next, we will write a GitHub Actions workflow that automates the testing and coverage reporting process for our Python project. This YAML configuration begins by defining the name of the workflow and specifying the triggers, which in this case are pushes and pull requests to the repository. We then set up a job named build that runs on the latest version of Ubuntu. The first step in our job checks out the repository's code, which is crucial to ensure that we are working with the latest changes. Following this, we set up Python by using a predefined action, specifying that we want Python version 3.8 for our environment. After Python is set up, we proceed to install necessary dependencies, specifically Pytest and Coverage, which are essential for running our tests and measuring the code coverage. The next step runs our tests with Coverage, allowing us to track which parts of our code are executed during testing. We then generate an HTML coverage report, which provides a user-friendly visual representation of our test coverage. Finally, we include a step to publish the coverage report using a simple HTTP server. This makes the report accessible to the team, enabling everyone to review the coverage and continuously improve code quality collaboratively. To conclude, generating HTML reports with Coverage.Py provides a sophisticated yet straightforward means of visualizing your test coverage. These reports help you see not only how much of your code has been tested, but also precisely which sections are missing coverage. By integrating this tool into your workflow, you can significantly enhance your coding practices. The ability to create tailored coverage reports, share them with your team, and incorporate them into CI/CD pipelines is incredibly beneficial as you strive to maintain high-quality code in your projects. As we continue our journey, we will transition into exploring continuous integration practices and how they can work seamlessly with our coverage tools for a more efficient development lifecycle. Happy coding, and don't forget to test. In this tutorial, we will focus on testing the command line interface, CLI, using mocks in Python. Testing is a crucial part of software development, especially when working with a CLI, which is a common entry point for users interacting with your application. Mocks allow us to simulate interactions with external systems or components, enabling us to validate our CLI behavior without relying on those systems directly. So far, we learned about the importance of generating HTML reports with Coverage.Py for visualizing test coverage in Python projects. We covered the installation and usage of Coverage.Py alongside Pytest to monitor code execution during testing. The session emphasized how to interpret coverage reports, identify untested code, and improve test coverage by adding appropriate test cases. Now, we will talk about testing the functionality of our CLI commands using mocks, which can help create more reliable and efficient tests. The first step in our journey into testing the CLI with mocks involves understanding what mocks are and how they can simplify our testing process. Mocks are objects that simulate the behavior of real objects in a controlled way. They allow us to specify the expected interactions and outcomes without having to rely on real external dependencies. For instance, If our CLI interacts with a database or an external API, using a mock allows us to run tests without needing the database or the API to be available. This is incredibly useful for consistent and repeatable testing. Now let's see how we can implement a simple command line interface, CLI application, using the click library to manage a list of cards. We start by importing the necessary package and then defining an empty list called cards to store our card names. The @click group decorator is used to create a main command group for our CLI where we can attach multiple commands. Inside this group, we define our first command, add, using the @cli command decorator. This command accepts an argument, name, which represents the name of the card to be added. When executed, the card's name is appended to our cards list, and a confirmation message is displayed to the user using click echo. Next, we implement the list command, which lists all the cards currently stored in our list. If there are cards available, the command prints each card in a formatted way. Otherwise, it lets the user know that no cards are available. Lastly, we wrap up our CLI functionality by calling the CLI function in the main section of the code, allowing our application to run when executed directly. With this structure in place, we have a solid foundation for our CLI that we can now test and expand upon. Let's explore how to implement tests for our command line interface, CLI application using the Pytest framework along with Click, which is tailored for testing CLI applications. Our initial step will be to create a new test file named test.cli, where we will outline our various test functions. In the test-add function, we make use of CLI-runner to run the add command, which simulates adding a card called myFirstCard. After executing the command, we check that the exit code is 0, signifying a successful operation. We also ensure that the output message verifies the addition of the card and that the card is included in the cards list. In a similar manner, the test_list_no_cards function calls the list command to examine the behavior of our CLI when there are no cards present. We anticipate the output to reflect the absence of cards and again check that the exit code is 0. Additionally, in test_list_with_cards, we clear any existing cards and then add 2 example cards, verifying that the output correctly displays these cards. Utilizing CLI-runner allows us to establish a controlled environment for effectively testing the functionalities of our CLI, showcasing best practices for application testing. Let's take a closer look at the test-add function. This test runs the command add with the argument myFirstCard, simulating adding a new card. The output is checked to ensure that the message confirms the addition of the card and confirms that the card is now included in the cards list. Similarly, the test_list_no_cards function checks that the output accurately reflects the state of no cards being available. If we have added any cards, we clear the cards list before each test using cards_clear. This ensures that each test starts with a fresh state, avoiding false positives. Now let's see how we can implement a test for our CLI that verifies the output when no cards are available. We modify the test_list_no_cards function by using the @patch decorator from the Unitist mock module. This allows us to replace the clickEcho method with a mock object. The purpose of this is to intercept calls to clickEcho, which is responsible for displaying output to the console. Within the test function, we first create an instance of CLI-runner to simulate the CLI environment, and then we invoke the list command. After checking that the command executed successfully with an exit code of 0, we employ the mock object to assert that clickEcho was called exactly once with the expected argument, no cards available. This verification step ensures that our CLI behaves correctly in scenarios where there are no cards to list. By incorporating this mock, we gain additional confidence that our application is working as intended while keeping the tests isolated from actual output interactions. This method of testing enhances the reliability and maintainability of our CLI commands. We will explore how to implement tests for CLI commands using the Pytest framework combined with Unitist mock. To kick things off, we'll create a test file named test_cli, which will contain our tests for the add and list commands. By leveraging the CLI runner from click testing, we can mimic command line execution within our tests, allowing us to assess the functionality of our commands. In our initial test, test_add, we execute the add command with a sample card name and verify if it runs successfully by checking that the exit code is 0. Additionally, we confirm that the expected output indicates the card's addition, and we ensure that the card is actually included in our list of cards. Subsequently, we will create methods to evaluate our list command. The test_list_no_cards function examines whether the output appropriately addresses the scenario when no cards are present, confirming that users receive a suitable message. To keep everything organized, we also reset the cards list before each test. Finally, we can improve the test_list_no_cards method by adding a mock to ensure that the output function, clickEcho, is called with the anticipated message, thereby validating the correct behavior of our CLI. Stay tuned for our next session, where we will delve deeper into automating tests for our CLI and integrating testing practices into our continuous integration. Now let's see how we can implement error handling in our CLI application. The first enhancement we make is to the add command, which allows users to add a new card. We start by checking if the name argument provided by the user is not just empty or filled with whitespace. This is done using the strip method, which removes any surrounding spaces. If the name turns out to be empty, we use clickEcho to display an error message indicating that the card name cannot be empty, and we exit the function early to prevent any further actions. Next, if the provided card name is valid, we append it to the cards list and confirm the addition with another clickEcho statement, which gives feedback to the user that the card has been successfully added. This simple validation not only enhances the user experience by preventing unnecessary actions, but also establishes a framework for more robust input handling within the CLI. By teaching our application to recognize and respond to invalid inputs, we ensure that users receive immediate, meaningful feedback while interacting with the system. Next, we will implement the remove command to facilitate the removal of a card by its name. This code begins by defining the remove function, where we use the @cli command decorator to register the command within our CLI application. The function accepts a single argument, name, which represents the name of the card to be removed. Now, let's take a look at the key functionality embedded in this command. We first check if the provided card name exists within the cards list. This validation step is crucial, as it prevents errors that could arise from attempting to remove a non-existent card. If the card is not found, we provide feedback to the user with an error message, clearly stating that the specified card does not exist. By returning early in this case, we ensure that the function does not proceed with the removal process. On the other hand, if the card is found, it is removed from the list, and a confirmation message is displayed, informing the user that the card has been successfully removed. This implementation not only enhances the user experience by providing clear feedback, but also ensures that our CLI behaves robustly, effectively handling potential error scenarios. Now let's take a look at the test we created for adding an empty card. This function utilizes the CLI runner from the Pytest framework, which allows us to simulate command line interactions for our CLI application. By invoking the add command with an empty string, we can effectively test how our application responds to invalid input. Next, we assert that the exit code is not equal to 0, which indicates that an error has occurred during the command execution. This is crucial as it verifies that the application correctly identifies the input as invalid. Following this, we check for the presence of a specific error message in the output. Error, card name cannot be empty. This ensures users are informed about what went wrong and can correct their input. Finally, we confirm that the cards list remains unchanged with a length of 0. This assertion is vital because it validates that the application correctly prevents the addition of an empty card, thereby maintaining the integrity of the data structure. Overall, this test not only checks for expected behavior, but also reinforces the application's robustness against incorrect user input. Now let's see how we can implement error handling for our remove command. In the test function, test remove non-existent card, we utilize the CLI runner to simulate invoking our command line interface. This allows us to run the remove command with a card name that does not exist in our cards list, specifically non-existent card. The beauty of this test lies in its ability to ensure our application gracefully handles this error condition. We assert that the exit code returned is not equal to 0, which indicates that an error has occurred, confirming the command did not execute successfully. Moreover, we check the output generated by the command to ensure it includes the specific error message. Error: card non-existent card not found. This validation is crucial as it informs the user of the exact issue they have encountered, contributing to a better overall user experience. By implementing such tests, we enhance the robustness of our CLI application, ensuring it communicates errors effectively and maintains reliability even in the face of user mistake. With error handling now integrated into our CLI application, it is crucial to ensure that mandatory arguments are enforced properly. The next step is to create a version of the add command that requires the name argument. By using @click argument name required equals true, we indicate to click that this argument must be provided by the user. If the user tries to run the add command without a card name, click will automatically display a helpful error message to assist the user in correcting the oversight. This method also improves the user experience by eliminating invalid inputs at the command level. Rather than allowing our application to continue running or fail silently, users receive instant feedback if they forget to include the necessary argument. This clarity ensures they understand what information is essential for the successful execution of the command. Once this code is implemented, it is vital to thoroughly retest our application to verify that the error handling functions as intended and that users are adequately informed about any missing inputs. This process will enhance the reliability and user-friendliness of our CLI, making it a more dependable tool for users. Now that we've discussed implementing error handling and testing, let's summarize the core takeaways. Error handling is a critical aspect of creating user-friendly CLI applications. It ensures our users understand what went wrong and how to fix it. We enhanced our existing code CLI by adding validations for input, robust error messages, and integrated testing for these error conditions. We utilized Click to streamline error management effectively, taking advantage of its features to ensure that users receive helpful feedback when they provide invalid inputs. Each test we created serves as a safety net, assuring that we maintain the expected behavior of our CLI regardless of the scenarios users might encounter. As we progress in enhancing the robustness of our applications, we will explore more advanced patterns, such as context managers and logging for better tracking of application states and errors. By investing in thorough testing and error handling, we establish a strong foundation for not only our current CLI application, but for any future projects we undertake. Stay tuned for the next lesson, where we will dive deeper into error logging and debugging strategies in CLI applications, ensuring that we can track down issues not just during testing, but also in production. In the ever-evolving world of software engineering, continuous integration, CI, stands out as a jewel among practices designed to optimize software development processes. By regularly integrating changes into a central repository, CI aims to enable teams to detect problems early and streamline their workflows. Today, we're diving deep into what continuous integration really means and how it has transformed the way developers work. So far, we've learned about implementing error handling in our CLI application to enhance user experience through informative feedback for invalid inputs. We added checks for empty card names and non-existent cards during the add and remove commands. Additionally, we integrated testing for these error conditions using Pytest and CLI runner. Moving forward, we will explore continuous integration in detail, focusing on its intuitive processes, benefits, and practical implementation. First, let's explore the historical context in which continuous integration emerged. In earlier software development practices, developers would work in isolation on separate branches of a code repository. This would inevitably lead to a natural buildup of changes that would require merging at a later stage. Can you imagine waiting weeks to integrate your code, only to face a mountain of merge conflicts? It wasn't just inconvenient, it was a recipe for disaster. Most merge errors would go unnoticed until extensive testing revealed them, leading to disruptions in production. For instance, if 3 different developers worked on the same codebase, they might diverge significantly from each other, creating complexity in ensuring that everything merged harmoniously. When integration finally occurred, these late-in-the-game discoverable errors would mean more time debugging and struggling over differences, all of which could be frustrating. This phenomenon sparked a revolutionary idea. Automation could drastically enhance the integration process. Therefore, continuous integration was born. Now let's take a look at a simplified continuous integration, CI, pipeline configuration, using a YAML file. This configuration specifies how the CI process operates when changes are made to the codebase, particularly focusing on the main branch. The first section outlines the triggers for the CI pipeline, indicating that it will activate upon any push or pull request made to the main branch. This ensures that developers receive immediate feedback on their code changes, facilitating swift identification of issues. Next, we define a job-labeled test that will run on the latest version of Ubuntu, showcasing cross-platform compatibility. Within this job, the steps delineate the actions that the CI system will take. Initially, it checks out the code from the repository, ensuring the pipeline has access to the latest codebase. Following that, it sets up the Python environment, specifying the desired Python version to maintain consistency. Then, the pipeline installs necessary dependencies, including Pytest, a critical tool for running tests. Finally, the pipeline executes the tests located in the tests directory. This setup promotes automation and reliability, allowing teams to enhance their workflow efficiency without manual testing interventions. By integrating this CI pipeline, developers can achieve faster iterations and higher code quality with each code chain. Now, let's take a look at the output generated by Pytest when we run our test suite. This output provides critical insights into the testing process, starting with the initialization of the test session, which sets the stage for executing our tests. Here, you can observe the platform and Python version used for the tests, ensuring that everything is set up correctly. As Pytest collects all the test cases, it provides a summary of how many tests are collected, which in our case is 10. The subsequent lines report the outcome of each individual test. For every test file, you will see a dot representing a pass test, offering a visual progress indicator as the tests are executed sequentially. In this instance, all tests have passed, leading to a perfect coverage score of 100%. This means that every line of code in your tested module was executed during the tests, confirming that none of the functionalities is left unchecked. Catching issues at this early stage saves developers from unexpected headaches later on, making this practice invaluable in maintaining code quality throughout the development process. This feedback loop is precisely what makes continuous integration effective. The quicker you know your tests pass or fail, the more informed your subsequent coding decisions can be. Now let's see how we can implement a basic tox configuration to enhance our testing workflow. This configuration begins with the tox section, where we specify envlist to outline the different Python environments in which we want to run our tests. Python versions 3.7, 3.8, 3.9, and 3.1. By defining these environments, we ensure that our code will be compatible across multiple versions, which is crucial for libraries and applications that aim to support a broad audience. Next, we create the test-env section, which defines the specifics for each testing environment. Here, we stipulate the dependencies required for our tests to run smoothly, primarily Pytest, a popular testing framework. The commands line instructs Tox to execute Pytest with the intended test directory as the argument, ensuring that we run our tests across each environment we defined earlier. With this setup, every time you push code to your repository, Tox will automatically create the necessary virtual environments and run the tests in each one, catching any compatibility issues that might arise. This automated testing cycle significantly boosts our confidence in the reliability of our code across different Python versions. Now let's implement coverage reporting in our testing setup using Tox and the Pytest-Cov plugin. First, we add Pytest-Cov to our dependencies in the Tox.Py configuration file, ensuring that it's available when we execute our tests. This plugin is specifically designed to track which parts of your code are being exercised during the test runs, providing insights into the overall test coverage of your codebase. By utilizing the Cov option followed by your module's name, Tox will execute the tests while simultaneously gathering coverage data. This allows you to see exactly which lines of code were executed and which were not, offering a clear picture of your testing thoroughness. Additionally, we can set a coverage threshold using the Coverage.Py parameter in our CI setup. This setting will ensure that if the overall test coverage drops below a specified percentage, let's say 80%, the CI pipeline will fail. This rule encourages developers to maintain a high standard of code quality, preventing code changes that might reduce the effectiveness of your test suite. In this way, integrating coverage reporting enhances both reliability and accountability within your development processes. Now, I hope this discussion clears up the why and what of continuous integration and Tox. You've seen how this practice can seamlessly integrate into your development process while ensuring quality and collaboration among your team, whether your team consists of one person or many. With CI systems actively taking care of testing and reporting, developers are free to allocate their time more towards innovation rather than fixing messes from the past. As we wrap up this lesson, the future seems bright for CI as tools evolve to make integration even smoother. In our next session, we'll shift our focus towards advanced patterns for error logging and debugging in CLI applications, helping us refine our robustness even further. So, there you have it. Continuous integration is not just a buzzword, it's a vital practice that can immensely improve productivity and quality in software development. Don't just take my word for it, implement it in your projects, and watch as the magic of CI unfolds before. Setting up Tox with GitHub Actions can streamline your testing workflows and ensure that your code is always in tip-top shape. Today, we're going to dive into how you can enhance your testing strategy with a seamless integration that not only automates your testing, but also promotes best practices in collaborative software development. So far, we've learned about continuous integration, CI, and how it automates the merging of code changes along with running tests, addressing historical challenges faced by developers. We've discussed tools like Tox and coverage reporting, which improve the testing process and ensure quality. Moving forward, we'll focus specifically on how to set up Tox with GitHub Actions, providing you with a robust framework for testing your Python project. Now let's see how we can implement a basic Tox configuration to establish our testing environments. The first step is to create a Tox.Py file in the root of your project. This file begins with the Tox section, where we specify the env list to include the Python versions we want to test against, namely Python 3.7, 3.8, and 3.9. This designates multiple testing environments that Tox will create for you automatically. Next, we define the test-env section, which is crucial for our testing setup. Here, we specify the dependencies required for running our tests, in this case, Pytest. This ensures that each isolated environment has access to the testing framework. Following that, we outline the commands directive, which tells Tox to execute Pytest when running tests. The beauty of this setup lies in its simplicity and power. Each time Tox runs, it creates isolated environments, installs the necessary dependencies, and executes the predefined commands, allowing you to efficiently test your code across different Python versions. This ensures robust testing coverage and compatibility for your project in various Python environments. Next, we will write the GitHub Actions workflow configuration in a file named Python-tests.yml. This file is crucial as it defines how our testing process will be automated every time a change is pushed to the main, branch, or a pull request is made. In this configuration, we first specify the name of the workflow and the events that will trigger it. Here, we've set it to run on pushes and pull requests to the main branch. This ensures that our tests are automatically executed, giving immediate feedback on whether the changes are stable. Now let's take a look at the jobs section, where we define a job-labeled test that will run on the latest version of Ubuntu. Each job consists of a series of steps. First, we check out the code from the repository, followed by setting up Python with the desired version. We then install tox using a simple pip install command. Finally, we execute tox, which runs the tests defined in our tox.ini file across the specified environments. This streamlined process allows for effective testing and validation of our code in a controlled environment, enhancing the reliability of our software development practices. Now let's break down each step in the GitHub Actions workflow to ensure you don't miss any nuances. First, the on section specifies the events that trigger the workflow. In this case, it's a push or a pull request to the main branch. Automating your testing processes on these events provides immediate feedback, letting you know if any changes affect your codebase's integrity. Next, we define a job under the jobs key. It encompasses all the steps needed to run your tests. Each step is executed sequentially, starting with the checkout code step, which uses GitHub's provided action to pull your latest code into the runner environment. Setting up Python comes next with the Setup Python step. It uses an action supplied by GitHub to allow you to specify which version of Python you want to install. Here, Python version 3x will always pull the latest 3x version available. However, for more control, you can specify major versions. After Python is set up, tox is installed in the environment, followed by executing tox. This runs all configurations specified in your tox.ini file, spinning up separate environments and executing your tests in each. Now let's implement the following configuration in your tox.ini file to enhance your testing setup. In the test-env section, we will specify the dependencies that tox should install for each testing environment. Here, we include Pytest for running our tests and Pytest-Cov for coverage reporting. By declaring these dependencies under the deps key, tox ensures that they are installed in the virtual environments it creates. Next, we will define the commands tox should execute for testing. The first command runs Pytest with the Cov option, which enables coverage tracking for a specified module in your project. This command will output a coverage report each time tox runs, helping you understand which parts of your code are adequately tested. Furthermore, we will enhance our coverage requirements to improve code quality. By adding the cov fail under equals 80 option in the command section, we enforce that if the test coverage falls below 80%, the testing process will fail. This safeguard ensures that commits lacking sufficient test coverage cannot be merged, thus maintaining high standards in your codebase. Now that you have a holistic understanding of tox and GitHub Actions, it's essential to bridge this knowledge into real-world scenarios. Let's say you added a new feature or fixed a bug. With tox and GitHub Actions working together, you push your changes, essentially triggering the tests. When your workflow completes, you're not just informed of failures, you're provided with precise indications for what needs fixing, leading to faster resolutions. But remember, automation is only as good as your testing coverage. A strong suite of tests covering edge cases, common user paths, and potential failures can significantly enhance the reliability of your application. Writing tests might seem daunting at first, but it's nothing less than an investment in your application's future. Are you starting to see how powerful this combination of tox and GitHub Actions can be? Imagine developing complex applications with confidence, ensuring that every commit is backed by running tests across diverse Python versions. By leveraging CI effectively, you can build robust applications that cater to different environments while simultaneously encouraging collaboration and accountability within your team. Wrapping it all up, you may now feel more comfortable setting up talks with GitHub Actions to ensure that your Python applications remain functional as you develop new features or fix bugs. As you continue to implement this process, you'll likely discover more tools that can enhance your testing strategies, but talks and GitHub Actions will form a solid foundation upon which you can expand. With the knowledge you've gained today, go ahead and implement talks in your projects alongside GitHub Actions. Empower your testing process and enhance the quality of your software, allowing you to focus on what truly matters, building great applications. Testing is a critical aspect of software development, ensuring that applications work as intended and maintain high-quality standards. In today's session, we're diving deep into the fascinating realm of testing scripts and applications, particularly focusing on practical implementations using Pytest. So far, we learned about the integration of talks with GitHub Actions to automate testing and enhance testing workflows in Python projects. We covered the installation of talks, the creation of a talks .ini file for defining testing environments, and how to set up a GitHub Actions workflow for automated testing upon code changes. Additionally, we explored how to view test results in GitHub Actions and enforce testing and coverage expectations with configuration adjustments. This process not only improves code quality, but also fosters collaboration and accountability in software development. Now, we will cover how to effectively test Python applications using scripts and frameworks like Pytest. Now let's see how we can implement our first test case using Pytest. We start by defining a simple function named add that takes two parameters, a and b, and returns their sum. This function is created in a file called math_operations.py. The simplicity of the add function makes it an ideal candidate for testing, allowing us to ensure that it behaves as expected. Next, we create a test file named test_math_operations.py. This is crucial because Pytest automatically recognizes files that start with test or end with test.py as containing test cases. Inside our test file, we import the add function from math_operations.py. We then define a test function named testadd, where we use assertions to verify that the outputs of our add function match expected results for given inputs. Each assertion checks a specific case, such as adding simple positive and negative integers. Lastly, to execute our tests, we run the Pytest command in the terminal. This command will automatically discover our test files, execute the defined test cases, and provide a summary of the results, helping us quickly determine if our add function works as intended. Now let's see how we can enhance our testing with a fixture in Pytest to streamline our tests for the addition functionality. We'll define a fixture called input_values, which serves as a reusable setup for our tests. This fixture returns a list of tuples, each containing two numbers along with their expected sum. By using this fixture, we can easily inject a set of predefined inputs into our test functions, promoting code cleanliness and organization. Next, we will write the testadd function that takes advantage of our input values fixture. Inside this function, we iterate through each tuple provided by the fixture. For each pair of input values, we assert that the output of our add function equals the expected result. This structure not only makes our tests concise, but also allows for easy expansion in the future. By utilizing fixtures, we are effectively managing our test environment, ensuring that our test cases remain clear and scalable, all while providing quick feedback on functionality. This approach illustrates the power of fixtures in enhancing clarity and reusability in testing. Now let's implement parameterization in our test cases to enhance our testing strategy. The @Pytest mock parameterize decorator is a powerful feature of Pytest that allows us to run the same test function multiple times with different sets of input parameters. In this example, we define three parameters, a, b, and expected, which represent the two numbers we'll be adding and the expected result, respectively. We then provide a list of tuples where each tuple consists of a set of values for these parameters. This setup enables us to run our test_add function once for each tuple without duplicating the test logic. When the test is executed, Pytest will automatically run test_add for each combination of values defined in the parameter list. This results in a concise and efficient way to verify that our addition function handles various cases correctly. Ultimately, using parameterization improves the readability of the tests and provides clear insights into the coverage and potential failure points, making it a preferred approach when dealing with multiple test scenarios. Now let's see how we can implement automated testing using GitHub Actions with a workflow configuration file. In this YAML file, we define the name of our workflow and specify that it should trigger on every push to the repository. The core of this setup lies within the Jobs section, where we designate a job named Test that runs on the latest version of Ubuntu. Next, we detail the steps necessary to execute the tests. The first step involves checking out the code from the repository, allowing the action to access the files for testing. Then, we set up a Python environment by selecting a specific version of Python, in this case, version 3.8. This ensures consistency across testing environments. Following that, we install the project dependencies, which includes upgrading pip and installing Pytest, the testing framework we are utilizing. Finally, we issue the command to run all the tests using Pytest. This streamlined workflow not only automates the testing process, but also ensures that all code changes are tested continuously, promoting a culture of quality and accountability in software development. Now let's implement a more informative way to handle assertion failures in our tests. In the provided code, we enhance the test_add function by adding a custom error message to our assertions. This is especially useful when dealing with multiple test cases, as it allows us to gain more context on what went wrong if a test fails. We iterate through a set of input values, which include pairs of numbers along with their expected sum. For each set of inputs, we assert that the result from the add function matches the expected result. If the assertion fails, instead of receiving a generic error message, we get a tailored message that specifies the exact inputs that led to failure, the expected outcome, and the actual result produced by the function. This level of detail aids significantly in diagnosing issues, especially in larger and more complicated applications, where a straightforward failure message may not provide sufficient insight. Incorporating custom messages into our assertions not only enhances our debugging process, but also instills confidence in our tests, making it easier to maintain and scale the application as development progresses. As we approach the conclusion of our exploration into testing scripts and applications, it's crucial to highlight the importance of maintaining code quality through a regular testing practice. Writing comprehensive tests is not just about catching bugs. It helps in understanding the code and maintaining confidence in the system, especially as projects grow and evolve. Remember, the more modular your code is, the easier it is to test. Adopt a test-driven development (TDD) approach if you can, where you write your tests before the actual implementation, ensuring that design and functionality meet the expected outcomes from the start. As you delve deeper into testing, don't hesitate to explore more Pytest capabilities such as mocking dependencies, measuring code coverage, and using plugins that extend functionality. The testing landscape is vast, and Pytest provides rich features to make your code resilient and maintainable. To wrap up, testing scripts and applications is a critical component of software development that should never be overlooked. Utilizing frameworks like Pytest provides you with the tools to create effective test cases, manage testing environments with fixtures and parameterization, and integrate automated testing in your CI pipelines. Armed with these techniques, you now have a strong foundation to ensure your Python projects are robust and reliable. Keep experimenting, keep testing, and make quality the cornerstone of your development. Now let's see how we can establish a virtual environment for our Python project using the built-in venv module. To create this environment, we first run the command Python mvenv, which initializes a new virtual environment named myenv in our project directory. This environment will contain its own Python installation, allowing us to manage dependencies separately from other projects. Next, to use this isolated environment, we need to activate it. Depending on your operating system, the activation command varies. For Windows, we use myenv /scripts/activate, while for Mac OS and Linux, the command is sosmyenv/bin/activate. Activating the environment modifies the terminal prompt to indicate that we are now operating within the virtual environment, meaning any packages we install will solely affect this environment. This process ensures that our project's dependencies do not conflict with others, allowing for smooth operation and improved test management. By following these steps, we lay a strong foundation for our development workflow. Next, we will write the command to install Pytest into our virtual environment. This is essential for setting up the testing framework that will help you run your tests effectively. By executing the command to install Pytest, you are fetching the latest version from the Python package index, PyPy, and ensuring it is isolated within your specific project environment, preventing version conflicts with other projects. Now, let's see how we can generate a list of all the dependencies our project requires. By using the pipfreeze command, we can capture all currently installed packages along with their specific versions. This is particularly useful for creating a requirements (txt) file, which serves as a roadmap for anyone else working on the project or for future reference. Finally, we will implement the command to install all the specified dependencies from our requirements (txt) file. This command reads the file and ensures that anyone who clones our project will have the same setup with all necessary libraries, making the environment reproducible and consistent across different setups. This practice is vital for collaborative projects to maintain reliability and ease of testing. Now let's take a look at how to organize our project structure and set up the Python for Pytest. The folder structure we need begins with a root directory containing 3 important elements: a virtual environment folder, a source code folder named src, and a test folder named tests. Inside the src folder, we place our main Python file, in this case, math operations, Py, which contains the functions we want to test. The tests folder will hold our test files, such as test math operations, Py, where we write the actual test cases. Next, we need to configure the Python environment variable, which helps Python locate our modules during testing. This is crucial, as it allows the test scripts to import the necessary modules seamlessly. On Windows, we set this path using the command setPythonPath = src, while on Mac OS and Linux, we use exportPythonPath = src. By doing so, we ensure that when we run our tests, Python knows to look in the src folder for any functions or classes that need to be imported, streamlining our test running process and ensuring everything is organized and efficient. Now let's take a look at how we can configure our Pytest environment through a Pytest-Ini file, which plays a crucial role in standardizing our test execution process. This configuration file, placed in the root of our project directory, contains specific settings that dictate how Pytest interacts with our test suite. In our Pytest-Ini file, we define several important sections. The test paths specifies the directory where Pytest should search for test files, helping it to streamline test discovery. In this case, we indicate that our test files are located in the tests directory. Next, the Python paths is configured to point to our source code directory, src, ensuring that all necessary modules are accessible during testing. Furthermore, the addops section allows us to customize the command line options used when running the tests. By setting it to vtb = shot, we enable verbose output for clearer test progress updates, while also adjusting the traceback formatting to be more concise, which can significantly enhance readability during test failure situations. With this configuration established, teams can ensure a consistent and efficient testing experience across all development environments. Now let's implement the following test case to demonstrate mocking in action. In this example, we're using the patch function from the unitist, mock library to replace the logging module in our calculator class with a mock object during the test execution. This approach allows us to isolate our tests by preventing any actual logging from happening, which keeps our test output clean and focused. As we proceed, we define a test function called test_addition_logs. Within this function, we first utilize the with statement and the patch function to create a mock for the logging module. This way, whenever the calculator class attempts to log messages, it will use the mock version instead. Next, we instantiate the calculator class and call its add method with two numbers, 5 and 3. We assert that the result of the addition is 8, confirming that our method works as expected. Finally, we examine the mock logging to ensure the info method was called exactly once and that it logged the intended message, added 5 plus 3 equals 8. This not only verifies our logging behavior, but also reinforces the utility of mocking to enhance our test reliability and performance. Now let's take a look at how we can set up our Docker container for the Python testing environment. We begin with a from instruction that specifies the base image for our Docker container, which is a lightweight version of Python 3.9. This ensures that our application has everything it needs to run in a minimal footprint. Next, we establish a working directory called app inside our container. This is where all subsequent commands will be executed. Following that, we copy our requirements txt file into this directory. This file is crucial as it contains a list of all the dependencies our application requires. We then run a command to install these dependencies without caching to minimize the final image size. After installing the necessary packages, we copy the rest of our application files into the container. The last part of our Docker file defines the command to be executed when the container starts. Here, we use Pytest to run our tests with a specific formatting option, providing clear output for any test results. This setup ensures a consistent testing environment that anyone on the team can use, effectively eliminating discrepancies between different setups. As we near the conclusion of our exploration into setting up dependencies and test environments, it's vital to understand how maintaining these practices contributes to the success of your Python projects. With structured dependencies, isolated test environments, and the use of testing frameworks like Pytest, you create a robust foundation for not only testing, but also for enhancing code quality in general. The effort you invest in a well-organized test environment pays off by streamlining your workflow, making it easier for you and your team to maintain, run, and scale tests as your project grows. The clearer your environment setup is, from dependencies to configurations, the lower the barrier for other developers to contribute effectively. So remember, make a habit of leveraging virtual environments, tracking dependencies properly with requirements. TXT, utilizing environment variables like pytho and path, and employing Pytest to its full potential using configuration files and mocking techniques. With these practices in place, you'll maintain a clean and efficient code base, and your testing efforts will be both rewarding and informative. In hindsight, establishing a solid groundwork for dependencies and test environments not only enhances the reliability of your tests, but also promotes collaborative code development. As projects grow, having these strategies ensures that everyone is on the same page and can contribute effectively. So, get started on setting up your dependencies and test environments, and watch your project evolve into a polished and maintainable piece of software, ready to tackle whatever challenges. Test failures happen. If they didn't, tests wouldn't be much use. What we do when tests fail is what counts. Debugging is a crucial skill for any developer, and in this tutorial, we will dive into effective strategies for handling test failures using Python's Pytest. We will explore various techniques and tools to identify and resolve issues, improve our testing process, and ultimately enhance the quality of our code. So far, we learned about the importance of setting up dependencies and test environments in Python projects. We explored the creation and activation of virtual environments, the management of dependencies using pip and requirements, TXT, and the configuration of Pytest for seamless testing. Additionally, we discussed mocking techniques to isolate functions during testing and the advantages of using Docker containers for consistent environments. Lastly, we reinforced that these practices are essential for maintaining code quality and enabling collaboration among developers. Now, we will talk about debugging test failures and the best practices to do so. Let's examine a function that serves to illustrate a common debugging scenario. The purpose of the listDoneCards function is to return a list of cards marked as done. However, for demonstration purposes, it currently returns none. This indicates a problem because our tests expect a list to be returned, and receiving none results in a failure. We will then create a test function named TestListDoneCards that invokes listDoneCards and verifies if the length of the returned list equals 2. Since listDoneCards returns none at this point, the assertion will fail. The error message will indicate that a none type has no length, which helps us identify the issue in our code. This scenario illustrates how to effectively approach debugging. By comprehending the expectations of our functions and their interactions with tests, we can improve our development and testing strategies, leading to more robust code in the future. Engaging with such scenarios enhances our analytical skills, enabling us to identify and resolve similar issues in our projects more effectively. Now let's take a look at how we can utilize Pytest's command line options to enhance our debugging process. One powerful feature is the L option, which displays local variables in the output alongside the stack trace when a test fails. This command can be run as Pytest-L, and if a test fails, it provides valuable context about the state of the code at the point of failure. For example, if we encounter a type error, indicating that a variable of type none type has no length, we can glean that the variable in this case, the list, was not initialized properly. Furthermore, we can enhance our debugging strategies with the PDB option. By running Pytest-PDB, we enter the interactive Python debugger when a test fails, allowing us to inspect variables and step through the code execution directly where the error occurred. This immersive approach helps pinpoint the exact root cause of issues, facilitating faster and more effective debugging. By leveraging these tools, we can streamline our debugging efforts and gain deeper insights into our code's behavior during testing. Now let's see how we can effectively utilize the Python debugger, PDB, in our interactive debugging sessions. In the debugging environment, you can use the command pthelist to inspect the current contents of the variable, the list. By executing this command, we can identify if the variable has the expected value, or, as in our example, if it holds none. This immediate feedback is crucial for understanding where our code might be failing. After inspecting the variable, you will often want to continue the execution of your program to see if any further issues arise. For this purpose, the command C is used, which allows you to continue running the code until the next breakpoint or until the end of the program. This process not only helps trace the data flow through the functions, but also aids in identifying if there are any other variables or states that could contribute to the issue at hand. By leveraging these PDB commands, you can quickly gain insights into your program's behavior, making debugging a more manageable and informative process. Now let's take a look at how to ensure our functions return a predictable output to avoid issues during testing. In this example, the function listDoneCards is designed to gather completed cards by calling another function, self, listCards, state equals done, which presumably retrieves the relevant cards. However, there is a possibility that self-listCards may return none if no cards match the criteria. To address this, the function implements a return statement that checks the result of the card retrieval. If doneCards is not none, it will return the list of cards. Otherwise, it returns an empty list. This approach is crucial in ensuring that subsequent parts of the code can operate on a consistent data type, namely, a list, whether or not there are any completed cards available. By returning an empty list when there are no cards to display, we mitigate the risk of encountering a type error in later operations that expect a list, thereby enhancing the robustness of our code and improving overall error management during testing. Now, let's take a look at using the LF flag in our testing process. This command instructs Pytest to rerun only the tests that failed during the last run. This feature is incredibly useful for quickly verifying fixes without needing to run the entire test suite, which can be time-consuming, especially in large projects. By focusing solely on the problematic tests, you can save time and make your debugging process more efficient. Next, we can enhance our debugging approach by combining the LF flag with the PDB option. This combination will take you directly into the Python debugger as soon as a failed test is encountered again, allowing you to examine the code in the context of the failure. This direct interaction with the debugger helps you reassess your logic immediately, investigating variable states and stepping through the code to identify the root cause of the issues. By strategically using these tools together, you can refine your debugging skills and improve your overall development workflow. We will explore the implementation of a test intended to verify the functionality of inserting an entry into a database. The test function, named test_database_insert, establishes a database instance by creating an object of the assumed database class. This organization facilitates the streamlined management of operations related to the database. In the course of the test, a sample entry labeled sample entry is inserted into the database. After this insertion, we invoke the fetchAll method to collect all entries currently stored within the database. This step is vital as it determines whether the insertion process was successful. To conclude the test, we execute an assertion to confirm that the number of entries returned equals 1. This signifies a successful test, confirming that the entry was accurately added to the database. It is noteworthy that, in the event of a test failure, we have the option to use the Pytest command along with the LF and PDB flags. This allows us to debug the process interactively, providing an opportunity to examine the database's state throughout the test execution. Such strategies underscore the importance of effective debugging within our testing workflow, which is essential for upholding code quality. Now let's take a look at how we can set up a database fixture using Pytest for our testing purposes. The purpose of a fixture is to create a controlled test environment that ensures a clean slate for each test. In this example, we define a fixture called setUpDatabase, which initializes a database object and inserts a sample entry into it. The yield statement allows us to run the test with this prepared environment, while everything after yield serves as cleanup code to reset the database afterward, ensuring that no residual state affects subsequent tests. Next, we have the actual test function, test_database_insert, which uses the setUpDatabase fixture. This function fetches all entries from the database and asserts that the length of the entries is 1, confirming that our insert operation was successful. This structure not only promotes reusable setups, but also guarantees that every test begins with a known state. By utilizing fixtures, we enhance the reliability of our tests, making them deterministic and reducing the risk of random failures due to lingering data or state changes from previous tests. Now, let's implement a test case that specifically addresses scenarios where the database might not contain any entries. We want to ensure that our code behaves correctly when faced with an empty dataset. In this example, we define a function called testNoEntries, which initializes a new instance of the database class. The first step within this test is to call the fetchAll method of the database class. This method is expected to return all the entries in the database, which, in this case, we anticipate will be an empty list. To test this behavior, we assert that the result of the fetchAll method is indeed an empty list. This assertion is crucial because it confirms that when no entries exist in the database, the method correctly returns an empty structure rather than raising an error or returning none. By ensuring that our code handles such edge cases properly, we create a more robust application and enhance the reliability of our tests. Emphasizing the importance of these checks helps us to build confidence in our code, as we can now be assured it can gracefully handle similar situations in the future. In conclusion, debugging test failures is a disciplined process that requires careful examination and systematic approaches. Utilizing Pytest's features like PDB, LF, and asserting with well-crafted tests lays a robust foundation for any Python codebase. By actively engaging in these practices, not only do we solve current problems, but we also build healthier code and bolster our skills as developers for the future. Remember, every test failure is simply a stepping stone to improvement, and with the right tools and mindset, we can overcome them. Thank you for joining today, and let's dive into the powerful world of debugging with Pytest flags. Debugging test failures is an essential skill for any developer, and Pytest provides a suite of command-line flags that can help streamline this process. Today, we will explore how these flags can aid in identifying and resolving issues in our tests more efficiently. So far, we learned about the significance of seeing test failures as opportunities for growth and refining our code. We covered how to analyze error messages and use Pytest commands like showlocals and pdb to debug effectively. Additionally, we discussed the importance of ensuring functions return predictable outputs and using fixtures for setting up controlled environments. Finally, we emphasized writing tests for edge cases to prevent future failures and maintaining a disciplined approach to debugging. Now, we will cover how to leverage various Pytest flags to enhance our debugging process, making it more intuitive and effective. Now, let's implement a simple function that calculates the average of a list of numbers. The calculateAverage function takes a single argument, numbers, which is expected to be a list of numerical values. Within this function, the average is computed by taking the sum of all elements in the list and dividing it by the total count of those elements, effectively giving us the mean value. Next, we will write a test function called testCalculateAverage. In this function, we will pass a list that includes a numerical value alongside a none value, which is purposely set up to trigger an error during execution. This is important for testing. By intentionally including an invalid input, we can observe how the function handles unexpected cases. The assertion checks whether the computed result equals 15, which is the expected average. However, due to the presence of none in the input list, running this test will raise a type error, thereby demonstrating how our code responds to edge cases. This lays the groundwork for understanding error handling in our functions and reinforces the importance of robust input validation in programming. Next, we will implement a crucial feature for debugging when using Pytest, the pdb flag. When you run your tests with the command Pytest-Pdb, it initiates the Python debugger right at the point where a test fails. This immediate access allows you to inspect the program's state and get a clearer understanding of the error. For example, consider a test where we attempt to calculate the average from a list containing a none value. When the test fails, the debugger prompt will display the line of code that caused the failure, providing valuable context. You can use various commands, like P to print the values of the variables currently in use, or L to list the code in the surrounding area, allowing you to see what might have gone wrong. This hands-on approach empowers you to step through your code interactively, giving you an opportunity to investigate issues and retrace your steps in the debugging process. By utilizing the pdb flag, you gain deeper insight into both the structure of your code and the nature of any failures, ultimately improving your development workflow. Now let's implement some simple test functions to illustrate how we can utilize the K option in Pytest. We begin by defining several test functions that represent basic arithmetic operations: addition, subtraction, multiplication, and division. Each function contains an assertion that checks if the expected result matches the outcome of the respective operation. For instance, the multiplication test verifies that multiplying 2 by 2 yields 4. Next, to focus specifically on the multiplication test without executing all the other test functions, we can leverage the K option. By using the command Pytest-K multiplication, we instruct Pytest to only run the test that matches the specified keyword, which in this case is the function test multiplication. This targeted approach allows us to efficiently debug the particular test we are interested in. It not only saves time, but also helps isolate issues, enabling a cleaner output without the clutter from unrelated tests. By focusing on a single test, we can better troubleshoot and refine our code, ensuring that our testing process is both effective and streamlined. Next, we will write the following command, Pytest-Lf, which stands for lost failed. This powerful flag is designed to streamline your debugging process by allowing you to rerun only the tests that failed in your last test run. Instead of sifting through your entire test suite, which can be time-consuming and inefficient, this command takes care of identifying and executing just those tests that encountered issues. For example, if you ran your tests and noted that 2 specific tests failed, simply executing Pytest-Lf will automatically run those 2 failing tests while skipping the others. This targeted execution is especially crucial during iterative debugging sessions, where you may address issues one at a time. By focusing solely on the tests that need your attention, you enhance your efficiency in resolving problems, enabling a more streamlined workflow. This approach fosters a disciplined process, allowing you to refine your test cases without the overhead of dealing with tests that have already passed, ultimately leading to a faster debugging cycle. Next, we will write the following command to leverage the maxfill option in Pytest. By executing Pytest maxfill equals 3, we set a threshold specifying that if 3 tests fail during our test run, the process will stop immediately. This functionality is incredibly useful, particularly when dealing with large test suites where numerous tests might be failing due to recent changes in the code. It enables you to concentrate on the most pressing issues without wading through a sea of failures that may not all be relevant at once. By halting at the first few failures, you can quickly address these issues and rerun the test suite efficiently. This focused approach not only streamlines your debugging process, but also maintains momentum in resolving bugs. Once you've tackled a handful of failures, you can confidently rerun all tests to ensure your fixes are effective and to catch any additional issues that might arise. Thus, integrating the maxfill flag into your workflow fosters a more efficient and objective debugging experience. Next, we will take a look at the verbose flag, v, in action to enhance the clarity of our test results. By invoking this option when running our tests, as shown in the command Pytest-V, we enable a detailed output that systematically lists each individual test along with its status, indicating whether it passed or failed. This structured approach to output allows us to quickly assess the state of our test suite. For example, in the output, we can see entries like test calculate, Py, test subtraction PASSED, and test calculate, Py, test multiplication failed. This format not only highlights any failing tests, but it also provides immediate insight into any areas that require our attention. By presenting results in this organized manner, the verbose flag helps us better understand the overall performance of our tests, making it easier to identify and address potential issues. Utilizing the V flag significantly improves our debugging workflow, transforming the test results into an engaging learning experience as we refine our code and uncover opportunities for improvement. In summary, leveraging Pytest flags can dramatically improve your debugging workflow. The showLocals flag provides context by displaying local variables upon test failure, while the PDB flag allows for interactive troubleshooting directly in the debugger. The K option enables us to execute specific tests. The LF option focuses on the last known issues. The maxfill flag prevents wasted effort on known failures, and the V flag gives insight into our testing status. With these tools at your disposal, you can embrace test failures confidently, turning them into valuable learning experiences. By refining your debugging practices through these Pytest flags, you are not just fixing errors, you're enhancing your programming skills and fostering resilient code. Remember, every failure serves as a stepping stone to your development journey, and with Pytest as your ally, you can tackle them head-on. Thanks for joining today, and as powerful as Pytest is right out of the box, it gets even better when we add plugins to the mix. Plugins enhance functionality, allowing you to tailor Pytest to your specific needs. Today, we'll explore how to find and use third-party plugins to supercharge your testing workflows. So far, we learned about the importance of debugging in development and how Pytest flags can enhance this process. We explored the show locals and PDB flags for gaining insights into test failures, allowing for easier identification of issues. Additionally, we discussed the utility of the K, LF, maxfail, and V flags for targeted and efficient test execution. Together, these tools help streamline debugging and transform test failures into learning opportunities. Now we will dive into the world of third-party plugins, how they can improve your testing process, and how to find and install them effectively. Now let's see how we can utilize the command line to browse available Pytest plugins in the Python package index, Py. With a simple command, we can search for plugins that enhance our testing capabilities. By entering the command pip search Pytest in your terminal, you will receive a list of packages related to Pytest, along with brief descriptions of each. This command functions effectively to help you identify plugins that align with your specific needs without the hassle of navigating the entire repository manually. Each displayed package includes relevant details, enabling you to make informed decisions about which plugins might best serve your project. Using this command is straightforward, and it serves as an efficient first step in discovering useful testing tools. Now let's see how we can install the Pytest-Cov plugin to enhance our testing capabilities with coverage reporting. The first command we'll run is to install the Pytest-Cov package using pip. This command will ensure that the plugin is downloaded and made available in our Python environment. It's crucial to run this command while making sure your virtual environment is active, as this keeps your dependencies organized and avoids conflicts with global packages. Once the installation is complete, we need to verify that the plugin has been successfully integrated into our Pytest setup. We can achieve this by executing the command that lists all active plugins recognized by Pytest. By running this command, we'll see an output that details all the plugins currently available, including Pytest-Cov. If it appears in the list, we can confidently say that we have added new functionality tailored for gathering test coverage insights, empowering us to improve our testing processes significantly. Now let's see how we can implement the add and subtract functions, which are fundamental operations we can use in our tests. These two simple functions in the calculations, Py file, are defined to perform addition and subtraction of two numbers. The add function takes two parameters, a and b, and returns their sum, while the subtract function also takes two parameters and returns the result of subtracting b from a. Next, we will write the tests for these functions in a new file called test calculations, Py. This file will include the necessary imports to access the functions being tested. Using the Pytest framework, we define two test functions, testadd and testsubtract. In testadd, we assert that calling add with the arguments 3 and 5 should equal 8, which checks if our addition function works correctly. Similarly, in testsubtract, we assert that subtracting 4 from 10 yields 6. By writing these tests, we not only confirm that our functions work as intended, but also set the stage for analyzing test coverage with the Pytest-Cov plugin, ensuring that we effectively verify the behaviors of our functions during the testing process. Now let's see how we can implement the Pytest-Django plugin for testing Django applications. First, you need to install the plugin using pip, which allows you to extend Pytest's capabilities for your Django project effortlessly. After installation, it's essential to configure your testing environment to recognize it as a Django application. We do this by creating a configuration file named Pytest, ini, in the root of your project, where we specify the Django settings module. Next, we can leverage Django's built-in testing tools to write a concise test for a model in your application. In this example, we create a test function that uses the @Pytest mock Django DB decorator, which indicates that the test will interact with the database. We proceed to create an instance of myModel with a specific name and immediately assert that the name property of the created instance matches the expected value. This validates that the model's behavior is correctly implemented. When the test is executed with Pytest, the Pytest-Django plugin ensures that a proper database environment is set up, allowing for reliable testing with ephemeral data, which maintains data integrity throughout the testing process. Now let's take a look at how we can implement a function that fetches data from an external API utilizing the requests library. The fetchData function is designed to take a URL as an argument and retrieve the JSON data from that endpoint. It achieves this by calling the requestsGet method, which makes a GET request to the specified URL, and then it returns the parsed JSON response. Next, we will write a test for this function using Pytest together with Pytest-Mock. This testing function, test-fetch-data, takes advantage of the mocking capabilities provided by the Pytest-Mock plugin. Inside this test, we use the Monkeypatch method to replace the actual requestsGet call with a mock object. This mock simulates the API response by returning a predefined JSON when the JSON method is invoked. This approach allows us to test the fetchData function without making a real network request, ensuring that the test is fast and consistent. Finally, we perform an assertion to verify that the result of calling fetchData matches the expected output, which in this case is a dictionary with the key and value. This method of testing enhances reliability while keeping external dependencies at bay during the test. Now let's implement a simple plugin that logs the execution time of tests in Pytest. We begin by defining a function called Pytest-Runtest-Macrepot, which is a special hook provided by Pytest. It gets called after each test is executed, allowing us to access various details about the test run. Inside this function, we check if the current phase of the test is the actual test execution, which is indicated by callWhen being equal to call. This is a crucial step, as we only want to measure the duration of the test execution itself and not the setup or teardown phases. Next, we calculate the duration of the test by subtracting callStart from callStop, where callStart is the timestamp when the test began and callStop is when it finished. Finally, we format the output string to indicate how long each test took to execute and print it out. With this straightforward implementation, you can now gain insights into your test performance, broadly enhancing your testing workflow. This foundation can be expanded further, for example, by saving the execution times to a log file or integrating them into a reporting tool for better analysis. In conclusion, plugins significantly enhance Pytest, making it a robust testing framework that adapts to your development needs. We've covered how to find, install, and use several popular plugins like Pytest-Cov, Pytest-Django, and Pytest-Mock. Each of these plugins serves to streamline your testing processes, making them faster and more informative. As you integrate plugins into your testing workflow, don't hesitate to explore and experiment with the plethora available in the Py repository. With the right plugins, you can transform the way you write and manage tests, ultimately leading to higher quality software. Embrace these tools and make your testing practices not just efficient, but also enjoyable. Running tests is a fundamental part of the software development process, but traditionally, it's something we do sequentially. This means each test waits for the previous one to finish before it starts. While this approach is straightforward, it can lead to significant slowdowns, especially in large test suites. In this segment, we'll explore how to run your tests in parallel with Pytest, speeding up your test execution dramatically. So far, we learned about the various ways plugins can enhance Pytest functionality, streamlining our testing processes. We discussed how to find and install popular plugins like Pytest-Cov, Pytest-Django, and Pytest-Mock, illustrating their practical applications in measuring coverage, testing Django applications, and creating mocks, respectively. Additionally, we touched on the possibility of creating custom plugins to tailor Pytest further to our specific needs. Overall, integrating these tools can significantly improve the quality and efficiency of our testing workflows. Now we'll cover how to run tests in parallel, making the most of our hardware resources. Now let's explore how to utilize the Pytest-Dist plugin for parallel test execution. First, we need to install the plugin to take advantage of its functionality. This can be accomplished easily by running the command to install Pytest-Dist through pip. By incorporating this plugin, we can effectively run our tests in parallel, thereby significantly reducing total execution time and enhancing productivity. Next, we will run our tests with the Pytest command using the N flag, which allows us to specify the number of CPU cores to utilize for parallel execution. For instance, if our machine is equipped with 4 cores, we would indicate this in our command. The Pytest-Cov distributes our tests across the specified cores evenly, enabling multiple tests to run concurrently. This concurrency mimics how a team of workers might tackle a job, allowing for faster completion of our test suite while maintaining a clean separation of tasks. It's an efficient way to leverage available hardware resources and ensure a more responsive development cycle. Now let's see how we can implement some basic mathematical operations as test cases to demonstrate the concept. In this example, we define 4 test functions: test add, test subtract, test multiply, and test divide. Each function simulates a time-consuming test with a time, sleep, 1, call, effectively pausing execution for 1 second to mimic a real-world scenario where tests may take time to complete due to computations or external resource access. Within each test function, we have simple assertions that verify the correctness of basic arithmetic operations. For instance, the test add function confirms that adding 1 and 1 yields 2, while test subtract checks that subtracting 1 from 2 gives 1. This straightforward structure helps establish a clear relationship between the test functions and their respective operations. To run these tests in parallel, we can utilize the Pytest command with the N flag, which allows us to specify the number of CPU cores to utilize. This enables efficient execution by running multiple test functions simultaneously, significantly reducing the total time required to complete the test suite. Now let's implement a fixture that sets up a separate database connection for each test, ensuring test isolation. This is crucial for parallel testing, as it prevents tests from interfering with each other when they manipulate shared resources. In the following code, we define a fixture named DB connection, which is responsible for creating an in-memory SQLite database that exists only for the duration of a single test. By using the @Pytest fixture decorator with a function scope, we guarantee that each test will receive a fresh database instance. The fixture opens a database connection, yields it to the test, and then closes the connection after the test is done. Next, we will explore 2 test functions: test insert and test delete. In test insert, we first create a table, insert a row of data, and then verify that the inserted value can be retrieved correctly. In contrast, test delete also creates the same table and inserts data, but it focuses on deleting the row and confirming that the table ends up empty. This approach effectively demonstrates how to maintain integrity and isolation while running multiple tests in parallel, allowing us to harness the efficiency of Pytest without running into conflict. Now let's see how we can implement the distribution of test cases across workers using the Pytest-Cov plugin. The command utilizes the N option followed by the number of cores we want to leverage, in this case, 4 cores, allowing for parallel execution of tests. The dist option enhances this command by specifying how the tests are distributed among the workers. When we set it to load, it evenly splits the tests across the available cores, which is particularly useful for test suites with varying execution times. This means that instead of the default load scope distribution, which tends to group tests from the same file together, using the load distribution can lead to more efficient use of CPU resources. Such an approach ensures that no single core becomes a bottleneck, while others are underutilized, leading to a more balanced and quicker test execution process. By adopting this command structure, we can optimize our testing strategy for speed and efficiency, harnessing the full power of our hardware resources. Now let's explore how we can effectively monitor test failures while running tests in parallel. The command integrates the maxfill option, which allows you to limit the number of failures that can occur before the test execution is halted. In this case, we've specified maxfill equals 5, meaning that if 5 tests fail, the testing process will stop. This feature is exceptionally useful for larger test suites, enabling you to gather insights from multiple failures in a single run without needing to redo the entire testing process. By setting a maximum failure threshold, you can allocate your debugging efforts more efficiently. It allows developers to quickly identify and resolve problems in their code base by showing them a broader picture of which tests are failing concurrently, rather than addressing issues one at a time over multiple test runs. The added parallel execution capability, invoked by the N4 flag, ensures that this process is swift and resource-efficient, utilizing up to 4 cores to run tests simultaneously. This combination of features significantly enhances both speed and insight, streamlining the testing workflow. Now let's implement a test for a function that simulates heavy computation while utilizing the benchmarking feature of Pytest. In the provided code, we define a test function called test-heavy-computation, which leverages the benchmark fixture. This fixture is essential because it automatically measures the execution time of the heavy computation function. Inside the test, we call the benchmark function, passing the heavy computation function as an argument to it. This allows Pytest to track how long the computation takes when executed. After running the benchmark, we assert that the result of the function matches the expected value, which in this case is 42. The heavy computation function itself simulates a time-consuming task by incorporating a sleep period of 2 seconds. This is a good representation of operations that might involve complex calculations or data processing that would typically take a noticeable amount of time. By structuring the test this way, we gather valuable metrics on the execution duration, enabling us to identify performance bottlenecks or slow tests during parallel execution, which can subsequently inform our optimization strategies. As we wrap up our discussion on running tests in parallel with Pytest, remember that the balance between speed and reliability is crucial. Utilizing Pytest-Cov to execute tests in parallel can significantly reduce test execution time and enhance your workflow. However, you must remain vigilant in ensuring that your tests are independent and only utilize shared resources in safe, controlled ways. By strategically organizing your tests, utilizing fixtures for isolation, and monitoring performance, you can enjoy the benefits of parallel testing without compromising the integrity of your tests. It transforms testing from a bottleneck into a pathway for rapid development and iteration, allowing faster release cycles and continuous integration efforts. Embrace the exciting functionalities that Pytest and its plugins offer, and leverage parallel testing to keep your projects moving at a brisk pace. Happy testing, and may your test runs be swift. In this session, we will dive into the creation of a Pytest plugin that automatically skips slow tests. This is crucial for maintaining an efficient testing workflow and can save significant time in larger projects. So far, we have learned about running tests in parallel with the Pytest-Cov plugin, optimizing our execution time by leveraging multiple CPU cores. Now, we will focus on enhancing our testing strategy further by implementing a plugin that improves our interaction with slow tests. Now let's implement the functionality that allows us to skip slow tests using Pytest. We start by defining a command line option, skip slow, using the Pytest adoption function, which lets users specify whether they want slow tests to be skipped when running the test suite. This option enhances the flexibility of our testing strategy, enabling developers to easily tailor their testing experience. Next, we turn our attention to the core of our functionality, the Pytest collection modify items hook. This powerful function comes into play during the collection phase of test execution. Inside it, we check if the skip slow option has been activated. If it has, we create a marker called skip slow that grants us the ability to skip tests. We then iterate through the collected test items, and if any test has been marked with the keyword slow, we apply the skip slow marker to that test. This way, those slow tests will be automatically skipped based on our defined behavior, enhancing the efficiency of the testing process. Now let's see how we can implement the slow test marker in our test cases. We will start by defining two tests, test example slow and test example fast. The slow test is decorated with @Pytest, mark, slow, which indicates to our plugin that it should be treated as a slow test. Inside this test, we simulate a long-running process using time, sleep, 10, effectively pausing the execution for 10 seconds to mimic a scenario that would delay feedback. This allows us to test how our plugin behaves when slow tests are included. Conversely, the test example fast function is a simple test that runs almost instantaneously, asserting that true is true, no delay is involved here. Adding the slow marker to test example slow is crucial for the plugin functionality. Whenever we run our tests with the skip slow flag, the Pytest framework will recognize this marking and skip the slow test efficiently. By employing this mechanism, we create a balance between thorough testing and maintaining swift feedback in our development workflow. This setup is vital for enhancing our testing strategy as we continue to develop and integrate our plugin. Now let's take a look at how we can implement a unit test for our plugin to ensure it behaves as expected. We begin by defining a test function named test_skip_slow_plugin, which uses the mocha fixture from the Pytest mock library to patch the method that retrieves command line options. In this case, we simulate the skip slow option being enabled by making this patched method return true. Next, we create a list of test items with a single slow test function named test_example_slow. This function is represented using Pytest function, allowing us to work with test items as if they were being collected by Pytest. We then call the Pytest collection modifitems function, which is the car of our plugin, passing none for the configuration and the initialized items list. After invoking the car function, we assert that our test item now has a marker indicating it should be skipped. Specifically, we check if the closest marker labeled skip is attached to the test, confirming that our plugin is correctly identifying the slow test for skipping whenever the skip slow option is utilized. This test validates the functionality we aim to provide with our plugin, ensuring it meets our expectations. Next, we will write the setup script necessary for packaging our plugin. The setup.py file is crucial as it contains metadata about our module, including its name, version, author information, and installation requirements. In this script, we define the name of our plugin as Pytest-Skip-Slow and set its version to 0.1. The author and author email fields provide essential information for users or contributors wanting to reach out for support or collaboration. To ensure that our plugin runs as intended, we specify that it requires Python's testing framework, Pytest, with a version equal to or higher than 6. Furthermore, we establish entry points in the configuration to inform Pytest about our plugin. The Pytest11 entry point indicates that when Pytest starts, it should look for additional plugins, and here we register our skip slow functionality, pointing it to our main plugin module, Pytest-Skip-Slow. Once this script is ready, we can easily install our plugin locally by running a pip command in the directory where setup.py is located. This installation method allows us to utilize the plugin's functionality across various projects seamlessly. Now let's implement the final steps for sharing our plugin with the community by uploading it to the Python package index, or PyPy. First, we need to create a distribution package that contains our plugin's code in a format suitable for distribution. We achieve this by running a command that generates both a source distribution and a wheel distribution, which will be saved in the dist folder. This is important because these formats are the standard for packaging Python projects, ensuring compatibility and ease of installation for users. Next, we take the generated packages and use a tool called Twine, which is specifically designed for securely uploading packages to PyPy. The Twine upload command allows us to specify the packages we want to upload from the dist directory. It's essential to provide your PyPy credentials when prompted, as this authenticates your account, allowing you to publish your plugin. After successfully uploading, your plugin becomes available for anyone to download and use, making it a valuable resource for developers looking to enhance their testing workflow with Pytest. In conclusion, we explored the process of creating a Pytest plugin that automatically skips slow tests. We defined a command line option to control which tests to skip, applied appropriate markers to our test cases, and ensured our implementation was robust through testing. We also discussed packaging the plugin for distribution and uploading it to Pytest-Cov. This plugin enhances the efficiency of your testing workflow, allowing developers to focus on faster tests while maintaining the ability to run or keep track of slow tests as needed. With the right tools and strategies in place, your testing experience with Pytest can be both efficient and effective, boosting your productivity and helping you deliver high-quality software faster. Thank you for tuning in, and I hope this session equipped you with the skills to build your own Pytest plugins. In this session, we're diving deep into the realm of advanced parameterized techniques in Pytest. These methods allow us to expand the functionality and flexibility of our testing scenarios significantly. So far, we've explored optimizing testing efficiency by creating a Pytest plugin that skips slow tests, defined command line options for test execution control, applied markers for test categorization, and developed a comprehensive testing strategy. Now, we will cover advanced parameterized techniques involving data structures, dynamic values, multiple parameters, and indirect parameterize. Now let's implement a test that transitions from using simple string values to passing instances of the card class directly as parameters. In the first example, we used a string to represent the card's starting state. Errors can creep in since string literals lack context. By parameterizing the test with actual card objects in the second example, we enhance the clarity and expressiveness of our tests. Here, we define a new parameter, starting card, which takes different instances of the card class initialized with various states. This approach allows us to directly work with the object-oriented features of Python, like encapsulation. As we add these cards to our database and finish their statuses, we verify that they correctly transition to the done state. This shift towards object parameterization not only improves readability, but also reinforces the intention behind our tests, a crucial aspect when maintaining test suites. However, keep in mind that each card state will need unique identifiers during test execution, which Pytest will handle, ensuring that our test cases remain isolated and easily understandable. This structured approach paves the way for more sophisticated testing methodologies. Now, let's implement a custom identifier function for our parameterized tests that enhances the expressiveness of our test case names. We define a function called cardState, which takes a card object as an argument and returns its state. This function serves to generate meaningful identifiers that reflect the different states of the cards being tested. Next, we apply this function in our @Pytest, mock, parameterize decorator under the ids parameter. The starting card parameter is assigned a list of card objects, which allows each test instance to be associated with a specific card state, such as to do, in prog, and done. This setup is crucial because, by utilizing object instances instead of simple strings, we improve the clarity and intent of our tests. Finally, when we run our tests, we will see the custom identifiers in the output, such as test ID functodO, PASSED, which clearly indicates the state being tested. This not only makes it easier to understand the results, but also aids in quickly identifying which specific scenario is being validated, ultimately leading to better maintainability and usability of the testing process. Now let's implement a dynamic approach to generating test parameters using the function textVariants. This function creates a dictionary containing various summary text styles, such as short, with spaces, and mixed case. By using Python's yield statement within a loop, it constructs Pytest param calls for each variant, providing a unique identifier for clarity during test execution. This is beneficial because it allows us to maintain a clear understanding of what each test case is verifying without cluttering our code with hard-coded values. In addition, the use of @Pytest, mock, parameterize allows us to associate these dynamically generated variants with the test summary function. As a result, each time the test runs, it receives a different summary variant. This method ensures that the tests are versatile and robust, adapting seamlessly to changes in the dictionary. Consequently, modifying the test scenarios becomes straightforward. Changes made to the variant's dictionary are reflected in the tests without the need to alter the test code. This enhances the maintainability of the test suite while allowing for meaningful assessments of how different summaries are handled. Now let's take a look at how we can effectively test multiple parameters using Pytest's advanced parameterized techniques. In this example, we define 3 lists that represent various attributes of a card: summaries, owners, and states. The summaries list contains different brief descriptions, while the owners list specifies the names of individuals responsible for the cards. Finally, the states list enumerates the potential statuses that a card can have. By applying the @Pytest, mock, parameterize, decorator 3 times, we create a comprehensive set of test cases that will cover every possible combination of these parameters. This cascading setup allows for rigorous testing, as it generates a total of 12 distinct tests when combined. 2 summaries, 2 owners, and 3 states lead to a robust matrix of scenarios that can be evaluated. Each test will add a card to the database with the given summary, owner, and state, then retrieve the card to assert its properties against the expected values. This method not only streamlines testing, but ensures effective coverage of various combinations, enhancing the reliability of our test suite. Now let's implement an indirect parameterized technique that enhances the functionality of our tests. In this example, we're defining a user fixture that is called indirectly based on the different roles that we want to test, specifically admin, team member, and visitor. The @Pytest, mock, parameterize, decorator is used to specify the different user roles that will be passed as parameters to our test function, test access rights. By setting the indirect argument, we inform Pytest to use the user fixture when these parameters are supplied, allowing it to handle the setup process appropriately for each role. Within the user fixture, we access the parameter using request_param, which reflects the role being tested. This allows us to print a message indicating that we are logging in as the specified role. The yield statement then enables us to return the role for the test execution while ensuring that subsequent cleanup, such as logging out, is handled after the test finishes execution. This streamlined approach not only enhances test organization, but also provides valuable contextual feedback for each role being tested, making the test output clearer and more informative. Now let's take a look at how we can utilize optional indirect fixtures to streamline our tests in Pytest. In the provided code, we define a fixture named user, which dynamically determines the role based on the parameter passed during test execution. By using getAttr, request, param, visitor, the fixture retrieves the parameter value if it exists. Otherwise, it defaults to visitor. This setup enables the same fixture to adapt seamlessly to both parameterized tests and standard tests without duplicating the underlying logic. Next, we see 2 test functions leveraging the user fixture. The first, testUnspecifiedUser, does not specify a parameter, so it uses the default role of visitor when the test runs. The second function, testAdminAndTeamMember, utilizes parameterization to test the fixture with different user roles, specifically admin and team member. By passing these roles as parameters and marking them as indirect, we ensure that the fixture applies the appropriate setup, logging the user in and executing the test context specific to their role. This approach simplifies code maintenance and enhances the clarity of test cases. Reviewing what we've covered, we've learned various advanced techniques for parameterize in Pytest. We understood how to use data structures and objects as parameter values, created custom identifiers for enhancing output clarity, generated dynamic values for flexibility, implemented multiple parameters for thorough testing, and utilized indirect parameterize for versatile fixture handling. Each of these aspects enhances our testing capabilities, making our suites robust and maintainable. Remember, with great power comes great responsibility. So use these techniques wisely to ensure your tests remain comprehensive and easy to understand. So, what's next? That's up for you to explore. Take these techniques and apply them in your testing environments. You'll surely find advanced parameterization to be a game changer in your Pytest experience. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to develop a comprehensive testing strategy using Pytest for the cards project, a simple task tracking command line application. You will start by cloning the repository and setting up a virtual environment with Pytest installed. Your main objective is to create an extensive test suite that covers key functionalities, such as adding, updating, completing, and listing cards. You should also handle edge cases by including tests for invalid inputs and states. Make use of Pytest fixtures for test environment setup, and take advantage of parameterization to run multiple input scenarios efficiently. Don't forget to integrate coverage measurement using the Pytest-Cov plugin, ensuring at least 80% code coverage. Documentation is crucial, so clearly describe each test's purpose and include a detailed README explaining how to execute the tests and interpret coverage reports. Additionally, set up a CI/CD pipeline with GitHub Actions to automatically run your tests when changes are pushed to the repository. Bonus challenges include using mocking, writing integration tests, and even developing a simple Pytest plugin. You can find the final project in the GitHub repository linked in the description. Good luck,